Hello, everyone. Welcome, and thank you for joining us today. I am Dr. Olufobi, and I'll be managing this session, so to say. So, our first speaker, which is one of the best papers for today, was not able to make it to get a visa. However, they will be joining us to do their presentation. So, we have our first speaker, which is Neo Lee, and the paper is ISCAN, a real-time CAN IDS with enhanced historical traffic learning capability. So, Neo is a graduate student at Zhejiang University and is going to be presenting the paper on behalf of his two professors, Professor Shogozu and Professor Ren Kui, who is also from the Zhejiang University. Their primary research is on the application of deep learning methods for anomaly detection in controller area network and also the Internet of Vehicles, the Internet of Things. And they are also interested in multivariate temporal analysis, prediction, and imputation. So let's hear them, and please, because this video they are not here, we have to ensure that they will be present for questioning. But let's try as much as possible to keep the room very quiet for the video. Thank you. Please go ahead.
Good morning, professors. I'm glad our paper was accepted by VehicleSec 24. Let me introduce our work, HistoCAN, a real-time CAN IDS with enhanced historical traffic learning capability. CAN bus protocol is widely used in in-vehicle network. However, it is not a security protocol. It operates on a broadcast system where any nodes can receive and manipulate messages potentially. It lacks authentication, making it unable to verify the identity of senders and receivers. The ID-based message parasitation scheme lacks inherent security and can be abused to manipulate the message flow, and its communication is not encrypted, making messages susceptible to sniffing. The CAN bus is exposed to various attacks, including DOS, fuzzing, spoofing, replay, and numerous unknown attacks. Thus, it is crucial to perform detection of CAN bus traffic. As shown in the bottom right corner of the slide, normal traffic flow and various types of attack traffic, such as DOS, fuzzing, spoofing, exhibit different patterns on a bitmap. This implies that we can extract patterns from bitmaps for anomaly detection. However, there are many challenges to do CAN bus anomaly detection. Exceptional to the known attacks, there are a lot of unknown abnormal data, and the abnormal data is extremely rare and heterogeneous compared to normal data. So, training the model to distinguish abnormal from the normal one poses a challenge. What's more, as we all know, in-vehicle networks require real-time monitoring and demand highly accurate detection for the safety of passengers and drivers. So, our goal is to detect unknown anomalies and do real-time and high-accuracy detection of CAN bus. And now I will introduce some key ideas of HistoCAN, from how to do real-time detection and how to learn a robust presentation of CAN bus traffic. An intuitive idea to achieve real-time detection is to reduce the computational complexity of neural networks. And the model can calculate it in parallel, so we need to design the model based on multi-layer perspection and convolutional neural networks architectures. In addition, we use neural networks to extract traffic features from both spatial and temporal dimensions, and fuse historical information to the currently extracted features iteratively to achieve robust and process detection. Here is the pipeline of our method. Firstly, the traffic data is encoded into bitmap and is shown in the blue field. Traffic features are extracted through special encoder and temporal encoder. Specifically, we design as convolutional neural networks to extract special features and multi-layer perceptrons to extract temporal features. And in green field, the extracted features are fused iteratively to historical features in order to capture long-term dependencies of CAN traffic data. Finally, decoder is used to reconstruct the input traffic, and mean square error is used to calculate the reconstruction error as anomaly score. The whole procedure was trained in self-supervised paradigm. The model was trained only by benign data, so it excels at reconstructing normal data and yields high anomaly scores for abnormal data. Our approach was validated on the car hacking dataset. HistoCAN surpasses all self-supervised baselines and is comparable to the performance of supervised learning baseline. And with historical information fused, HistoCAN exhibits better performance in detecting attacks like DOS attack, which are prone to deceive reconstruction-based methods. In addition, our method can achieve real-time and robust detection. We use kernel density estimation method to process the car hacking dataset. The x-coordinate represents the number of frames per second, and the y-coordinate represents the density. It can be seen that the rate of CAN frame is below 2000 frames per second most of the time, as shown in the table at the bottom left. The detection speed of HistoCAN reach over 2600 frames per second even on general CPU, achieving real-time monitoring. And as shown in the bottom right table, HistoCAN was able to achieve accurate detection even when we reduced the training data by half, which proves the robustness of our approach. So in conclusion, we design hybrid encoder and make it for CAN bus traffic representation from spatial and temporal perspectives. And we design a historical information fusion module that can preserve historical information iteratively when detecting traffic. The proposed CAN bus anomaly detection method is capable of unknown attack detection, real-time and accurate anomaly detection. Thank you.
Any question? Yes.
One question I had was, how do your model detect unknown attacks?
Pardon, I didn't recognize your. Could you repeat your question again? Sorry.
So in your paper, you had detection of spoofing attack, fuzzing attack, etc. How do you detect unknown attacks?
Oh yes. I train my model only with benign data, and so my model can only know the pattern of normal data. So when he meets the abnormal data, sorry, I forgot the premise. I do anomaly detection based on reconstruction method. It means if my method only knows the normal data pattern, so he can reconstruct the input data well. And if our model meets the abnormal data, a data pattern he never made before. It fails to reconstruct it. So I set the anomaly scores as the subset of the input and the reconstructor output. And as I mentioned before, our model only knows the pattern of normal data. So when it meets abnormal data, the reconstruction error is very, very high. So I can say it is abnormal.
Thank you, Neil. Yes.
Can I ask another question?
Yeah, go ahead.
Hi, this is Mert Peace from Clemson University. So I really appreciate this work. One question I have while you're presenting it, so you evaluated it like using CPU and GPU to see if it's real-time capable, which is a fantastic thing that you've done because a lot of other work doesn't do that. What kind of CPU did you use for this, and did you like use any automotive grade ECUs or CPUs, or was it like a regular desktop computer, like an Intel-based chip? Thank you.
I use Intel's 7th generation CPU.
So it's an Intel, right?
Yes, it's Intel.
Okay, thank you.
Thank you, Neil. I have a question, actually. So, for this method, do we need to run it for each car model, or it is universal for every car? Because we know that the messages that comes from each car CAN model is different.
Yes, as we know, the CAN frame is different from different vehicle factories. So when we deploy it in different car, we should retrain it once again. It is not universal.
Thank you. Thank you. Thank you. Let's appreciate the speaker again. Our next presentation is reverse engineering of multiplex CAN frame. And the presenter is Dr. Alessio Buscemi. Alessio received his PhD from the Faculty of Science and Technology and Medicine at University of Luxembourg. And he served as a postdoctoral researcher at Second Lab, working on reverse engineering of CAN bus traffic and time-sensitive network for automotive Ethernet. Currently, he's a software engineer at LifeWire. Let's welcome Alessio.
Hello. I cannot see very much the slides. Oh, okay, so, thank you. Hello, everyone. As said, my name is Alessio Buscemi, and today I will present reverse engineering of multiplex CAN frames, which is a work in collaboration with Professor Engel, also from the University of Luxembourg, and Professor Kang Shin from the University of Michigan, who's also in the room. Now, this is the outline of the presentation. I will shortly introduce CAN multiplexing and present our work on reverse engineering of CAN multiplex data, proceed with the performance evaluation, discuss the security concerns related to CAN multiplexing, and to reverse engineering of multiplexing, and finally we'll draw some conclusions. Now, most of you may be familiar with the CAN bus, which is the de facto word standard for in-vehicle communication. And a CAN frame is composed of multiple fields. The ones that we are interested in are the ID and the payload for this work. Now, the data in the payload, its format, it's kept secret from the general public by the OEMs. Each OEM has its own format for the data. And this data is a true mine for valuable mine for information regarding the vehicle status. And therefore, if we want to retrieve this information, we need to apply reverse engineering. So we have seen that there is a new way of representing the information in CAN, which is multiplexing, which, contrary to the base assumption of CAN, which basically all the frames with the same ID include the same set of signals, so we can follow the actual behavior of the signals throughout the frames represented by the same ID. In the case of multiplexing, actually, different set of frames can be represented by the same ID. So what does this mean for reverse engineering? It means that it fails on producing the tokenization step on this sort of data, because the base assumption of the tokenization is that you can identify the boundaries of the signals based on the behaviors of their bits, which is not the case because there is no more coherence in the behavior of the bits, given that they represent different sets of signals that also have different positions within the payload. So we have two types of multiplexing, simple and extended, where simple, we have just one multiplexer signal, which is the signal that defines what is the content of the rest of the payload, so which set of signals is being represented. And extended, we have sort of hierarchy of multiplexers. In this paper, we have addressed both of them. Now, we have designed and implemented CAN multiplex translator, or CAN MXT for short, which is our tool to reverse engineer CAN multiplex data. The way we envision it to be embedded in a current reverse engineering system is basically between the data collection and the tokenization step. So we collect the trace and we assess whether we split the trace in subtraces, one for each ID, and we analyze each ID independently. If we find that the frames associated with the ID are not multiplex, then we proceed with the standard tokenization. Otherwise, we identify the multiplexer and we decompose in additional subframes. So basically one series for each multiplexer. And then we tokenize each subseries independently. On the left, you can see an overview of the algorithm, which of course is way more articulated in the article. Now, to evaluate the performance on CAN MXT, unfortunately, we couldn't evaluate this on vehicles on the roads, as to the best of our knowledge, there is no CAN multiplexing yet on commercial vehicles. So we couldn't collect data in the real world, and therefore we had to design our own tool to generate synthetic traces starting from real standard CAN traces. So we designed CAN multiplex frames generator, or CAN MXG for short, which receives in input 4 parameters, which you find on the right, which are percentage of eligible frames to multiplex. So we cannot multiplex all data within a standard CAN trace. And therefore, we define how many of the eligible frames we want to multiplex. Multiplexing type, so either simple or extended. The max number of subframes, which means the max number of multiplexers that can be associated with the same ID. And the bits behavior. So we think that given that the multiplexer signal is within the first byte, the behavior of the other bits in the same byte may influence the performance of CAN MXT. So we have either static, dynamic, or half dynamic bits. Now we collected 3 traces, thanks to a pick and tool on a Peugeot 108, Peugeot 208, and a Renault Capture. And we also got 2 traces from the public Recon repository, which were the Alfa Romeo Giulia and the Opel Corsa. And from these 5 traces, which were collected under real world scenarios, we generated, according to, of course, different combinations of the 4 parameters that I mentioned, almost 2,000 synthetic traces. And this composes our test set. For the evaluation metrics that we adopted, given that true positives are the number of multiplex IDs correctly identified as multiplex, the false positive are the number of IDs corresponding to standard IDs incorrectly identified as multiplex, and false negatives are the number of multiplex IDs incorrectly identified as non-multiplexed, we adopted 4 metrics. I guess you all know precision and recall, and we also designed 2 new metrics for these specific words, which is base period accuracy, which is basically the number of IDs whose base period has been correctly identified divided by the true positives. The multiplexer type accuracy, which is the number of IDs whose multiplexer type has been correctly identified divided the true positives. And as we can see here, we achieve a pretty high recall and precision, as well as base period accuracy, which basically certifies that when we correctly identify frames as multiplex, also we guess their base period correctly most of the times. And also, for the multiplexer type accuracy, we see that it largely depends on the behavior of the other bits in the first byte. So we achieve quite high results for, in the case of dynamic bits, and the worst results in half dynamic. And why this is the case is mostly left to future work. So we said that the whole purpose of this work was to understand whether it's still possible to reverse engineer multiplex CAN frames. And therefore, what we did was, let's try to use CAN-MXT plus a state-of-the-art algorithm, which, as I said, will start at the tokenization phase. And what we can see that indeed, CAN-match, which is one of the state-of-the-art reverse engineering tool, basically never managed to address the correct tokenization of multiplex data by itself, but thanks to CAN-MXT, actually achieves performance that are very similar to its performance on the original trace, so without multiplexing. Now you may wonder, how is this connected to security? The reason is, as I said, this data, CAN data, are very valuable, especially for aftermarket companies. But of course, there is a reason why the OEMs tends to achieve security through obscurity. It's because they don't want to reveal the format of this data. That can be used for malicious activities. So similar to other reverse engineering tools, this can be used also by adversaries to facilitate the work and the effort and time that they spend. So we believe that despite having done a good job for aftermarket companies for the next generation of in-vehicle data, again, we can use CAN-MXT also for malevolent purposes. Of course, also these thoughts are more articulated in the paper, and I would be also happy to discuss with you in person today. These are the conclusions we drew. So baseline, we urge OEMs to secure in-vehicle communication. This is a partial bibliography. The rest you find in the paper. Thank you for your attention. Looking forward to hearing your questions.
Thank you. Do we have any question for Alessio? We can accommodate one question. We can accommodate one question.
Real quick, one question.
Yeah, go ahead.
Hi. Really great work. Very interested. Want to follow up and talk to you about it in the context of the Pivot data sharing project that I'm involved in, but was wondering if you're making any of your data or tools publicly available.
All right, thank you for your questions. So the plan was to make CAN-MXG, so for the generation of synthetic traces in order to help the community to generate the traces and then study and maybe even improve CAN-MXT. Regarding CAN-MXT, maybe we will also open source, but we'll let you know.
Okay, great, thank you.
Thank you.
Thank you so much. Let's appreciate the speaker. Our next talk is a work in progress paper, which is a trust assessment method for in-vehicle network using risk assessment. And the presenter is Arthur Hamann, and is a research assistant at the Institute of Distributed Systems at University. His research area is security and privacy in vehicle network and vehicle-to-everything communication. So he holds a bachelor's degree and a master's degree in computer science from ULM University. Let's welcome the speaker.
Do I also have a pointer here somewhere? But a pointer that I can show on the slide? I'm not sure about it, just only one back. Okay. Okay, great. Hello everyone. As already mentioned, I'm Arthur Hermann. I'm a PhD student at Ulm University in Germany. And I'm presenting here our work about trust assessment in vehicle network based on vehicle risk assessment. And as you can see here, in vehicle networks are today already quite complex systems of systems. And therefore, there are quite long information flows, such as the one from the GNSS ECU providing position data to the vehicle computer. For illustration purposes, this one is now quite short, but in real-world systems, we have quite long information flows. And this makes the data vulnerable to tampering, because in any of the ECUs and in the communication flows, the data could get compromised. And if we have a safety-critical application running in the vehicle computer, which is using the position data, this can, of course, lead to safety incidents. There exist, of course, many security mechanisms already in in-vehicle networks, such as an intrusion detection system. But they are often located in different components of the vehicle and work independently of each other. And this makes it difficult for the application running in the vehicle computer to determine if the received data is trustworthy, because the vehicle computer just does not know which security mechanisms are, for example, implemented in the GNSS ECU, and if malicious activities were detected there, and what the consequences would be. And here comes the Trust Assessment Framework, or for short, the TAF, into play. It is located in the vehicle computer and basically models all trust dependencies in the data flow of the position and of all other ECUs where other data flows exist. So for the position, the trust dependencies would look like this. As we are using subjective logic in our TAF, these trust dependencies, which is here these omegas you see between these nodes, they are subjective logic trust opinions. So they have a belief, disbelief, and uncertainty value. And for example, this omega between the vehicle computer and the zonal controller would then represent how much the vehicle computer trusts the zonal controller, that the zonal controller is not compromising the position data. And based on these three opinions, these three omegas, the TAF can then calculate the opinion from the vehicle computer to the position, and this final opinion is then used to decide if the position is trustworthy and can be used by the application, or if it's compromised. And in our work here, we focused now on how we can calculate a trust opinion from an ECU to another ECU, so such as this one here. And here, many different aspects can be taken into account. And we used the implemented security controls, which are implemented in the zonal controller, because depending on the implemented security controls, the risk of the ECU being compromised would differ, and therefore this should be taken into account when it comes to the trust assessment of the ECU. Our approach is divided here into a design time and a runtime part. At design time, a threat analysis and risk assessment is done, or for short, ATARA. This is a standardized approach where basically the risks are determined for the ECU, for which the trust opinion is calculated. And in addition to that, also the security controls are determined to mitigate the risks. For each risk, then also the risk levels are provided, which basically describe how severe the risk is. And based on these risk levels, then weights are calculated for each security control, which define how important these controls are. Also, based on these risks, design time trust opinion is already calculated, which describes basically the minimum belief and disbelief in the ECU. At runtime, it is then checked which of the security controls are actually implemented in the system, and based on the design time trust opinion and the weights, the final opinion on the ECU is calculated. I want to showcase this now in a very simple example. So let's assume that these are the security controls provided by the TARA and the corresponding weights. We start at the trust opinion calculated at design time, which you see on the right side. So there's the minimum belief and disbelief. And if a security control is now implemented, which we know from runtime evaluation, based on the weight, the belief will be increased by a certain amount and the uncertainty will be reduced. If a control is not implemented, the disbelief will be increased. And this is done for all security controls, so that at the end, we have the opinion, in this case, from the vehicle computer to the zonal controller based on the implemented security controls. I want to go now back to the slide which I showed at the beginning of the presentation. And the question, is the position now trustworthy? For this, we only need these trust dependencies we showed at the beginning. And for the first opinion, this is the one we just calculated. The other ones could be calculated by similar approaches. And based on these three opinions, we can now calculate the trust opinion from the vehicle computer to the position. And based on that, we can derive a probabilistic value. And this value is now compared to a threshold value, which has to be specified. And as our value is bigger, in this case, the TAF would decide that the position is trustworthy and can be used by the application. If the left opinion from the vehicle computer to the zonal controller has now a high disbelief because many security controls are not implemented, in this case, the TAF would decide that the position is not trustworthy. So in this case, based on the TAF and the calculated opinions, it will be decided if the position should be used by the application or not. Finally, I would like to draw a very brief conclusion. In our work, we described an approach for trust opinion calculation on ECUs in in-vehicle networks based on the output of ATARA and implemented security controls. We showed the feasibility in two different scenarios, and in future works, we would like to adopt this approach to V2X networks and also take the output of security controls into account for the trust assessment. That was it so far from my side. Thank you for your attention.
Thank you. We have a question?
Hi, I'm Maggie Shipman from Southwest Research Institute. If you go back to slide 21, you talked about several security controls and deciding the weight of each. How was the weight decided for MACsec compared to Secure Boot?
Yeah, it's a good question. What we are doing is basically we are taking the output of the TARA and the corresponding risk levels which are attached to each risk which was defined by the TARA. And what we are doing here is that we are comparing these risk levels if the specific security control would not be integrated in the system and this specific security control would be integrated into the system. And then we have two different risk levels with and without a specific security control integrated into the system. And based on this knowledge, we will derive the specific weight for this specific security control. The concrete formulas for the calculation of these weights are in our paper.
Okay, thank you.
Sure.
Any other question? I have a question actually.
Sure.
We know that heavy vehicles, they are quite different from the normal autonomous vehicles that we say have most of these ECUs. Can this approach be used on those as well?
You're talking now about using it within the vehicle or also for V2X communication?
For V2X communication.
For V2X communication, that's one thing where we are working on at the moment, and we believe on that, yes, we can use this. We somehow have to integrate the knowledge about an external vehicle and the risks which are in this external vehicle into our ego vehicle for this calculation. This is something where we are working on because we cannot assume that for each vehicle on the outside, we as the ego vehicle know which risks are going on there. And how to exchange this knowledge, this is something where we are working on.
Oh, thank you. Let's appreciate the speaker again.
All right, so welcome to session 2B. So I'm Hyungsa from Purdue. We have two presenters for this session. The first presenter is Evan Allen. Evan is a graduate student at Virginia Tech. He is mainly working on in-vehicle network security by using the reverse engineering and developing the cyber tools. So in this talk, he will mainly discuss about the distributed firewall for zonal networks.
Hello, everybody. My name is Evan, and today I want to talk about how we can make it significantly more difficult for attackers to remotely attack vehicles by using firewalls. Remote attacks are real. They have been since 2015 or even a little earlier, but they still are today. Even just in 2023, people are still getting into Teslas over Bluetooth, and that's not good, right? We don't want that. So imagine this example scenario where you have an attacker who wants to stop your car while you're in it against your will. What they might be able to do is remotely compromise one of the ECUs in your car, such as the infotainment or head unit, and this has actually happened. And then they can send, for example, a braking message to the wheel and stop your car. So we can all agree in this scenario, that message, we would call it malicious. But I would argue we should be calling it invalid. Because in most vehicle architectures, it doesn't even make sense that this should be possible. Why should your head unit ever be sending a braking message to the wheel? It doesn't even make sense in most architectures. So can we make a list of what kind of behavior we want to allow in our car? What is something that should happen? Well, we can kind of do that in a really simple way with just a security policy, where a security policy is just a list of all the possible messages that we think should be allowed to occur in the car. So each message would have a sender, a type, and a receiver, where the type is just some number, like a CAN arbitration ID, that describes what the message is. If the message is in the policy, it's authorized, and we expect it to occur. But if it's not in the policy, it's unauthorized. At design time, we've stated we never think this should happen. And ideally, we would block it. So for example, if the person hits the brake pedal, that's normal, and it'll send a braking message to the wheel, and we want to allow this, so we would have it in the security policy. But in our malicious scenario, if the attacker compromises the head unit and sends a braking message to the wheel, that's a message that should not ever happen. So it wouldn't be in our security policy, and ideally, we would block it. We can use this to create a threat model for our attacker. Suppose that our attacker wants to accomplish some malicious goal, like G, like stop the car. They've compromised some ECU, C, but that ECU C can't accomplish their goal directly. So instead they have to send some message M to a different ECU, T, like a target, and that one can accomplish their goal. In this threat model, we're going to make the assumption that the message that they want to send is not one that we would ever expect to happen at design time. So in other words, it wouldn't be in our security policy. As a defender, our goal is to enforce the security policy. Block the messages that we don't expect to happen, which would stop attacks like this one. But what do we need to enforce such a security policy? It's two things: authentication and authorization. Authentication tells us who's the real sender of this message, because the message has a sender, a type, and a receiver information, but the attacker could lie, they could spoof their sender. We need some way to know it for sure. Authorization is saying once we know the true values of the sender, the type, and the receiver, how do we know if it's allowed? How do we know if it's in the security policy and we should allow it? A common approach to doing this that's very common in the literature, even though it's not really described this way, is with cryptography or message authentication codes, or MACs. The idea here is that ECUs will append a MAC to each of their messages using a cryptographic operation, and then another ECU can use that MAC to verify who sent it. But the problem with this is that cryptographic operations are slow, especially on resource-constrained ECUs like you'd find in a car. And that's a problem, because some data in vehicles must travel at over 40 megabits per second with less than 0.1 millisecond of latency in some cases, which is really hard. And you can reach that speed with more expensive hardware cryptography, but putting that in every ECU is expensive, it's hard. You have to standardize it, you have to make all your suppliers do it, and there are tons of other issues with that, like making all of your ECUs know your security policy. What if we could try to avoid it? There are firewall-based approaches as well in the literature, and that's what I want to talk about today. It's becoming more popular over the past couple of years, especially in some companies. The idea is just block unauthorized messages within the network based on a set of rules. This is attractive because it can operate very fast at line speed with low latency sometimes, and it lets you centralize your security burden to a few network devices within the network instead of all the ECUs. For this talk, we're going to assume this environment, which is a switched zonal topology. Every ECU is connected with a one-to-one connection to a zonal gateway where there's one for each physical zone of the car. If you've worked with real cars, you know this is not how it looks right now. There's CAN buses and FlexRay and other things going on. But I want you just to imagine, what if your car did look like this one day in the future? Because automotive Ethernet is becoming more popular. What could you do with this? Well, for one thing, we can notice that every single message between ECUs must flow through the zonal gateways, which means that these zonal gateways in the middle, we can use them to enforce the security policy if we can trust them. We can block the messages that we don't want to flow because it's like a central choke point. The zonal gateways enforce the security policy. Again, they have to accomplish both the authentication, is S the true sender, and authorization. Is it allowed in the security policy? For authentication, this topology makes it almost by default, because if you have this switched network, then when a message comes from an ECU into a zonal gateway, the zonal gateway knows for sure which ECU it came from because it's on that one interface. There's literally only one thing on the end of that wire. And likewise, ECUs know that the only thing that could have sent them a message directly was the zonal gateway. So this lets them effectively offload their security burden to the zonal gateways. So if you can have the zonal gateways block bad messages, the ECUs don't have to worry about it as much. You can implement this very quickly using TCAMs, or ternary content addressable memories. TCAMs are very fast memory modules that allow you to look up entries based off of the data in the entry. So here you can just have an allow-deny table of what messages are allowed and not, basically from your security table, the security policy. If you have TCAMs on each of your zonal gateways, and you have one looking at all the messages coming in on each interface, you can start to enforce our security policy. So, for example, on a single interface with the ECU connected to it, if a message comes in, we just check, does it match one of these entries? So I'll give you an example. We can use this to block message spoofing, because let's say the head unit gets hacked by the attacker and wants to send a message, but pretending it's the brake pedal with a false sender value. Well, the TCAM table on that zonal gateway, you can configure it so it only has allow entries where the sender is the head unit. So when this spoofed message comes in with a false sender, it just doesn't match any of the allowed entries, and it's blocked, basically automatically. And then if the sender doesn't spoof the message, they still can't send unauthorized ones because it's also not an allowed entry in the TCAM. And finally, the allowed messages just go through really quickly because there is an allow entry and it passes. And TCAMs are very fast. Every single lookup takes a single fixed low latency, and they can operate at line speed. To test out how well this worked performance-wise, we created a simulation of an in-vehicle network with a similar topology to this using a tool called OmNet++. And we gathered data from a bunch of different other papers and sources about what a vehicle network might look like in this case, as well as what kind of packet flows you would have going on, and created this table of packets going different places. We compared our method to a baseline no security case with nothing extra, as well as two high-speed, lightweight cryptography methods that are one of the fastest that we could find, SIP-hash and SHA-20 poly 1305. Both of them you can use to create a message authentication code of various lengths. We found that when we looked at the latency of all of our data flows, so each group of columns is a data flow, our method produced latency that was just barely over the no security case, but far below the latency produced by actually creating and verifying the cryptography tags. And in some of these cases, actually, the cryptography tags, they violated the deadline of those packets. If we look closer at the latency as an effect of packet size, we can see that when we're trying to send control data traffic with very low latency deadlines, such as 0.1 milliseconds, having a TCAM firewall lets you send up to 750 bytes in a packet, whereas the lightweight cryptography techniques immediately lower you down to like around 4 bytes or so, if that. Of course, this method has many limitations. One, it requires that the zonal gateways are trusted. We can create such a security policy, although I'd argue that doing so is just good to do anyway. And that you have this topology. We don't prevent every attack, and we couldn't try it on a real in-vehicle network because we didn't have the money. But the biggest one is that TCAM space is limited and it is expensive. However, I do think that with enough work, the distributed nature of our system would let you partition the security policy into a very reasonable amount of TCAM space. But the big takeaways that I want to convey are this. TCAM firewalls can block many attacks with very little overhead if you can manage it. And they're much faster than even the most lightweight cryptography methods out there. They require almost no changes to your ECUs, which make it way easier to get components from suppliers and cheaper. And they also let you manage your security policy in one single place, the gateways. But most of all, I just want you to consider your network topology and your architecture make a huge difference on what security options are available to you and how efficient that they can be. So even if you can't go with this topology, because I know you have many other factors to consider, I'd like you to at least think about it when you look at the trade-offs in your next design. Thank you.
All right. Are there any questions from audience?
This is Amir from Denso. I had a question. What kind of implications does a TCAM system have for dynamic updates to firewall rules? Thank you.
Yeah, so you mean like on the fly or just like an update after the car's been produced? So, I mean, really, if you can configure the TCAM from like remotely, like as a manufacturer, then you could change the policy. And that's another reason why this is really useful, because if you want to change your security policy, before it would be you have to go to all of your ECUs and change what they would do. And oftentimes that wasn't even a standardized process. Like this security policy, it's a way of looking at it, but people have been using it for a long time, just not calling it that. You just might have an ECU with a hard-coded rule. If the sender's this, allow it, you know. But this would mean that now when you want to change a rule, you can just do it at the zonal gateways. So if you have some architecture in your vehicle and your manufacturer pipeline so that you're able to access that over the air, then sure, you could.
Thank you. All right, so yeah, our second speaker is Professor Stefano Longari. Stefano is an assistant professor at Politecnico di Milano, and his core research focus is offensive and defensive security for cyber-physical systems. So in this talk, he will mainly talk about evaluating adversarial attack against the intrusion detection system.
Okay, thank you very much for the introduction. So yeah, what we're going to present right now is a study on the feasibility of evasion attacks against intrusion detection systems, and specifically, I'm expecting this is the forward command. Yeah, but it's not moving. Sorry for the interruption. Okay, perfect, now it's working. Thank you, sorry. So we were talking about evasion attacks against intrusion detection systems, and specifically we're going to focus on intrusion detection systems on CAN. I don't want to bother anyone with the whole story about CAN. We all know what we want and what it is. Now, my main point that I want to focus on is that being an onboard intrusion in an onboard network, it has two characteristics that I care about. The first one is that packets are usually periodic, and the second is that the payload of CAN messages is often composed of sensor data, so sensor signals, right? Now, we have throughout the years demonstrated over and over how unsecure this network is, and specifically those sensor data have been used to demonstrate attacks throughout. I would say the most evidence are 2016 ones from Miller and Balasek. Now, the point is that throughout these years, we've also defined a lot of solutions, a lot of proposals for countermeasures. Of these, the majority is focused on intrusion detection. And in the last few years, we've had a lot of proposals, and I'm also guilty of this, on machine learning-based intrusion detection systems. Now, these systems are actually becoming kind of effective. The results are promising. However, before, they focus on two things. The first one is they focus on anomaly detection often, which means that they recognize the standard behavior of the network, and they consider everything that is not that behavior as anomalous, right? And second, they consider the signals inside the payload and evaluate those throughout a time. So they consider, for example, the last 40 packets on the network and evaluate whether and how the signals change in those packets, right? So these machine learning-based intrusion detection systems, even if they are becoming kind of effective, are vulnerable to a new type of attack, which, new for the specific context, which is adversarial attacks, right? Adversarial attacks, and specifically evasion attacks, are attacks that are meant to send an attack payload in such a way that the payload remain effective, but the intrusion detection system does not realize that that is an attack payload. It considers it a normal packet. The simple example is the most famous one is the one of the panda. We all see a panda in both images, but an image classificator in the first case considers the image a panda. When the attacker perturbs the image with some apparently random noise, the effect is that the classificator recognizes it as a gibbon. We want to do the same thing on CAN. And actually, why is this? Sorry. Okay. We want to do the same thing on CAN. And to do this, we actually take the approaches from the state of the art on other contexts and apply them to the automotive environment. So the idea is that the attacker has a moment in which he wants to inject attacks on the bus. He takes the current traffic on the bus. He adds the attack packets, and then he feeds this to what is called an oracle. An oracle is an intrusion detection system that is controlled by the attacker, and the attacker uses to understand whether the payload is currently detected or not. If the oracle detects the attack, the attacker passes this through an evasive algorithm, and we have implemented 3 versions of common and famous attacks, which evasive algorithms, which are BIM and deep fool. And this modifies slightly the packets that have been implemented as an attack, and then these are fed again to the oracle. If the oracle detects them, this cycle goes on. If the oracle does not detect them anymore, or after a given amount of iterations, the packet is then sent on the CAN bus. And our goal here is not really to define the best approach, but to understand whether it is actually feasible, given these intrusion detection systems, to evade them through evasive attacks, right? So to do this, we have designed 6 intrusion detection systems. 2 of them are autoencoders, which mean that they try to reconstruct the same packet, specifically a feed-forward neural network, which only reconstructs the last packet on the bus, and another, which is Candito, which is a previous work from ours, that is an LSTM autoencoder that attempts to reconstruct the last 40 packets on the bus. On the other side, we have 4 predictive models, 2 LSTM and 2 OGRUs, which basically consider a window of packets from the bus and attempt to predict the next packet. So our evaluation focuses on 4 elements, which is the effectiveness of the evasion, or is it actually possible to implement these evasive attacks? The effectiveness of the perturbation, as in we have seen a panda in both images, are we actually going to see an attack in both cases, or the perturbation changes the attack towards something that is not an attack anymore? Transferability of the attack, which means now we don't always have the knowledge about DDS that has been used for detection. Can we use a different oracle and still obtain evasion? And finally, and this we will discuss slightly later, is it possible to pre-compute the attack? Now, the problem here is that, as I mentioned before, the attacker needs to feed the oracle the attacks, then he needs to give this to the evasive algorithm, and this cycle needs to go through for a bunch of times, depending on the easiness of the evasion process. This has to be done, ideally in real time, while the network packets are passing, which is unrealistic. So the approach that we have found that is possible is actually to pre-compute this attack and inject it when we find a similar sequence. Now let's see the results. The first, the table is one of many. What I want to highlight is that basically the results highlight that aside Candito, all the other intrusion detection systems that we have defined are actually pretty easily evaded. More than 50, the recall drops of more than 50%, sometimes 70%. On Candito, which is effectively the one that we use from the state of the art, this drops a lot to more or less 9 to 10% of recall drop. However, even if these are effective, the question that we'll still have to ask is it actually still an attack, right? Are we actually generating an attack or not? Now, these 2 images are 2 examples. We had to evaluate this case by case, but I want to show you what may happen. So in the image on the left, what you're seeing in both is the value of a signal throughout time, throughout the attack sequence. The green line is what we would expect to see if there was no attack, so what the intrusion detection system doesn't classify as an attack. The orange dotted line is the attack as it was designed by the attacker. The blue line is what happens when you perturb the attack to make it evasive. So in the first case, as you can see, the blue line is identical to the non-tampered line. So basically, this is not an attack anymore. We have perturbed the message so much that this is not an attack. In the second case, instead, we have found some instances where the attack actually remains an attack while not being detected. Now, on transferability, we have tested an intrusion detection system with different oracles, and we have found that amongst our intrusion detection systems, the most effective one to be an oracle for others is the LSTM. The LSTM keeps a 40% transfer rate, which means that evasive attacks that are considered evasive by the LSTM are actually, in 40% of the cases, evasive also for the other intrusion detection systems. And interestingly, the LSTM is actually a better oracle for Candito than Candito itself. Now, the reason behind this is actually, it makes sense when we consider that we have only 50 iterations available for each packet, because in the best case scenario, with all the time in the world, the attacker would always want to have the white box attack where he knows exactly the intrusion detection system. And finally, On attack pre-computation, as I was mentioning, the problem is we need to be sure to find a way to implement the attack in real time, but if we have to do 50 iterations of Oracle and evasive algorithm, this is not feasible. This does not become feasible. So the only option that we have at this point is to build a fully evasive sequence before, understand what is the preamble on the network of that fully evasive sequence. The preamble is basically what is before that, because the intrusion detection systems will check not only the attack, but also what is coming before it. They will consider, say, 40 packets. Maybe 20 packets are the part before the attack, and 20 packets are attack packets. So we take these sequences that we found fully evasive in a specific moment, we take the preamble, and we search for a similar preamble throughout the dataset. And we have found two different cases. So the first point to highlight is that to have an effective precomputation and transfer, we need to have around 90% of the packets in the preamble identical to the ones that we had in the right moment, in the evasive moment. Now, depending on the type of ID, we have two options. For slowly varying signals, this is really common. It's super easy to inject attacks that we pre-computed on slowly varying signals because they tend to have repetitive behavior. And so we find often that, that same preamble throughout the dataset. For others, so more not really slowly varying signals, this is really much more randomic. And it depends on whether we find a similar situation in the future from the attack. Now, this would mean that for an attacker, what we would have to do is to pre-compute multiple possibilities given different preambles and then find the one that is consistent. But nonetheless, it is actually feasible. Okay, so I've actually finished pretty fast. In conclusion, sadly, the conclusions are not final because we definitely saw both options in all the tests. We have found that it is possible to evade, to build evasion attacks, but we have also found that it is really hard for an attacker to effectively implement them with the exact goal that it had on all IDs. We are only capable, for example, to pre-compute them in specific cases, right? So we do not have a final answer. We do not have a final answer on whether evasion is effectively feasible in the real world. And for this, we're going to focus on two things in the future work. The first one is the way in which implemented attacks is fixed. They are 25 packets attacks. What we would like to work on is to build an attack sequence that takes all the time needed by the attacker to slowly drift from the set point that the normal behavior would have to the set point that the attacker wants to have. And the second is, as I was mentioning, Candito, which is the state-of-the-art algorithm that we tested, the only one from the state-of-the-art that we tested, seems to be robust. Now, a relevant question is it robust because it is a strong intrusion detection system, or is it robust because given the network that it uses and the approach, it is actually maintained robustness? So what we would like to do is find other state-of-the-art algorithms, implement them, and understand whether they retain the robustness that we expected from Candito, or there are some, say, networks that we decide and we define will not be good intrusion detection systems, especially because they are affected by evasion attacks. With this, I finished. Thank you very much for listening.
Is there any question from audience? Maybe I can ask a question. So, in order to detect attack, first we need to know what is normal scenario and then what is abnormal scenario, right? But I believe that it is hard to consider all possible normal scenarios. So do you have any idea and thought?
So our approach to this has always been, this is one of the biggest problems, I would say, from the academic point of view, because we do not have infinite data sets, right? So our approach is try to understand which are the elements from an attack that trigger, the elements, from the normal scenarios that trigger detection. This is something that we have already done, and try to understand how those cases have been happened, let's say, in the normal scenario, and try to re-implement them, try to reproduce those with the vehicle in order to have a lot of different data sets that actually cover all those things that may look like an attack, but they are not, and then train again the algorithm at a second moment, yeah. But that's definitely still an open question, I would say. Thank you.
Okay, yeah.
Thank you very much.
Okay, this is end of the session 2B. Thank you so much.
Hello. Good afternoon. I wish there was a little coffee break or something after the keynote. I don't know, like listening to somebody for an hour is, in my opinion, very tiring. Yeah, well, welcome to session 3B, Vehicle Network Security, Part 2. I'm going to be your session chair today. We have, let me see, we have 4 papers today. And a little quickly about me, if you don't know me, I'm Mert Peace from Columbus University, assistant professor there. Our first speaker is going to be Sharika Kumar, who is the cybersecurity leader at Accelera, which is owned by, or which is a business unit of Cummins. She's also a part-time PhD student at The Ohio State University, go blue, focusing on automotive cybersecurity. And without further ado, Sharika?
Thank you, Mark. Thank you, everyone, for your time coming into this session. So the topic that I'm going to talk about today is security attacks to name management protocol in vehicular settings. Before we dive into the topic, I would like to introduce the authors. Like Mark said, I am Sharika Kumar. I work full-time at Cummins, and I'm also a part-time PhD student under Anish Arora. He's the chair of Computer Science Department at The Ohio State University. For this paper, we have collaborated with postdoc researcher Imtihaz Karim and Professor Elisa Bertino from Purdue University. So trucks play a crucial role in the transportation system that any small security events can lead to a major social impact. And in medium and heavy duty trucks, the vehicular networks are primarily based on SAE J1939 networks. And this protocol came into existence at a time where security was not a primary consideration while designing the protocols. So hence, leading to various security gaps in these protocols. And also, on top of this, the inherent gaps of the CAN adds to more attack surfaces in SAE J1939. So in this paper, we characterize the vulnerabilities of name management protocol. We uncover 19 new stealthy attacks, and to our knowledge, we are the first one to do formal security verification on medium and heavy duty vehicular networks. So we also validated the impact on real trucks and on bench setups. So you can see in this demonstration, we are using our poisoning attack to disable radar on a moving truck, resulting in disabling of blind spot detection or lane keeping features of a vehicle. So you can see the alert came that the radar is disabled. In today's session, I would like to start with scope, background, and dive into how we approach to solve this problem. And we would like to discuss the attacks found and conclude with discussion and future work. So basically, originating in United States, SAE J1939 recommended practice is split into 7 layers, ISO OSI layers, with presentation layer and session layer absent, like any bus protocol. And for this paper, we focused on SAJ 1939-81 network management layer, which defines the messages for network management and defines the arbitration process which the controller application or the devices on a vehicle would use to win and to participate on a vehicular network. The name management protocol, basically, like any devices on a vehicle network, begins participation on a SAJ 1939 network by announcing the source address and the name onto the network. So that is like, say I'm brake at source address X. The first message that I would send out on the network would be my source address in the CAN ID field and the primary function in the data field as name. And sometimes the devices also store a source address name association table reflecting the current status of various devices connected on a in-vehicle network. So on power on or on request, a controller application, for example, ECM on source address 00 would send out an address claim message and wait for contending claims. So in case of a contending claim, for example, retarder on the same address comes in, the address arbitration is performed by looking at the name field name. So basically, the lower the numerical value of the name, higher is the priority. So if a controller application is not able to win the arbitration, it should indicate the inability to claim the address by sending a cannot claim address. And the device who wins the arbitration can now use the address to continue the normal communication. Another scenario is like a controller application seeing collisions or bus off would delay, add a pseudo-random delay and reclaim the address and continue participation on the network. So since this state transitions and the name management protocol came into an existence when security was not the primary consideration while designing, there exists like lack of security authentication between the controller application, lack of name contention, and usage of less secure methods like checksums instead of mags, etc. So the model checking is actually a commonly used verification technique which has two inputs, finite state machine and property. So property is basically expressed as linear temporal logic, which describes the order of behaviors and the various addressing schemes in the name management protocol, such as like single address capability and arbitrary address capability, was modeled in SVM as finite state machine and inputted into a model checker in new SM. And this model checker is nothing but a decision block which scans through the state space and looks for an intersection. So if the properties are holding good for a specific model, it is confirmed as valid. And in case the model checker finds an intersection, that means there is a scenario that exists where the property is not holding good for a particular model, and which will result in a counterexample. And the counterexample would be the path, the sequence of actions basically for an attack. So basically, we validated our attacks by verifying like crucial properties such as a controller application should always reach the state of S5. And if it doesn't reach, you can see, and if a controller application gets stuck in between S1 and S3, then that would be a counterexample. So when we detect a counterexample, we again disable this counterexample to investigate if there is any more counterexample. So you can see there exists another counterexample which would deny a controller application to reach the S5 and to actually start broadcasting or using the source address and be on the network. So combining the power of human inspection and formal verification, we found 19 new stealthy attacks which we classified based on the attack style, and we have tabulated the cybersecurity properties like confidentiality, integrity, availability that was violated, and also we have tabulated the sequence of actions. So for the sake of this presentation, we are only covering 4 attacks that we have found. So this is a simple pre-play attack. So basically any controller application trying to participate on an SAE J1939 network, the address arbitration would be based on the priority of the name field. So you can see 5 controller applications are on this network, and here the attacker comes in and records the claims and pre-plays them before the legit claims, such a way that when the legit devices come in, they are denied from network participation. So this also led to entire vehicle startup denial. So you can see I'm trying to, okay, that video is not playing. Okay, so basically here you can see like I'm trying to key on, okay, it's coming, but the vehicle is not starting up. So the next attack we have is the source address name table poisoning attack. So any receiving controller application that receives an address claim message is supposed to compare and record the claims and build a source address name association table. So in our name table, source address name table poisoning attack, the attacker comes in and sends destination specific claims to poison the source address name table and with this attack we were able to actually disable ABS from on a moving truck, which would result in heartbreaking for an operator. So the next attack that we had was the birthday attack. So in the commanded message in name management protocol, there is an 8-bit checksum that is used to ensure that the receiving controller application is correct. So exploiting the fact that checksums are inadequate for security purposes and they are prone to collisions, we exploited them and we fabricated this brute force birthday collision attack where we impersonated as a commanding ECU and brute force the entire checksum range 0 to 255 and assigned new names of to the controller applications that's on the network. So this resulted in multiple source addresses or like devices having the same name and the correlation being broken. And this scenario is not detectable as the protocol does not handle name contention. The next attack we had in this paper was denial of service with collision attack. So basically, each of the controller applications or some of the controller application in the vehicle had like weak entropy sources to generate random numbers. So we exploited the predictive nature of the random numbers, and we accurately predicted the time that an engine controller would put a claim message on the network. So by predicting this time, we were able to repeatedly collide with the claim messages, denying that device from network participation. So we used picoscope and oscilloscope to confirm that the collisions are working by verifying that the CRC validation is failing on these messages. So this attack was actually very difficult to achieve, and this is the bend setup that we used, which consists of an adversary, an engine controller, and a pecan logger connected via SA-J1939 network at 250 kbps. So we visualize the events in a claim and its response to derive temporal offset for adversarial collisions. So we basically predicted the exact time that the actual claim will come, and we injected the claim to intentionally collide with the claim. So this is a pick a card, any card attack. So any arbitrary address capable device has the ability to choose from an source address of 128 to 247. So in this attack, what we did is, like, as an adversary, we went in and claimed on all source address in this range of in between 128 to 247, and we omitted one particular source address, forcing the legit controller application to take that source address. So as an adversary, we were controlling the source address that an arbitrary address capable device would take, and this helped the attacker to no longer do network discovery and to execute targeted attacks on that particular controller. And the discussion is like, even though our attacks were proven on medium and heavy duty trucks, these are not limited to medium and heavy duty trucks. It is applicable to anywhere where there is an SA-J1939 network, like agricultural equipments, forklift, industrial equipments. And the defense against our attacks is to have stronger authentication mechanisms and also processing claims only by global address, because in our attacks we were bypassing the SA-J1939 imposture detection and alert message by using destination specific claims, and also using non-repeatable secure random numbers in the controller applications. Our attacks is also possible on CAN-FD networks because name management protocol messages are excluded in J1939-22. So including the NMP messages in 22 can defend our attacks in CAN-FD networks, and also addition of name contention in the name management protocol, and replacement of checksum with MAC would also put in stronger mitigation mechanisms. So our future work includes expanding similar approach to other SA-J1939 protocols and implementing practical key exchange and key derivation algorithms for onboard vehicular networks. Thank you.
Thank you. One question, maybe.
Ahmed Surush from Zux. I was curious what percentage of the attacks you found were actually like a meaningful contribution of the model checker versus the ones that you could see by a human could see due to the lack of the protocol level security features.
Yeah. I think most of the attacks came out of human inspection, and we had 3-4 attacks that came out of model checker, and we used model checker more like a validation to prove out attacks. And some of the attacks we were able to demonstrate on our real trucks, and whatever we couldn't, we just verified using the model checker.
I see. Thank you.
Thanks.
Thank you, Sharika. And let's continue with our second talk today. We're going to actually have two presenters for this, namely Wentao and Sam. Wentao Chen and Sam Dare. They're both undergrads at UC Irvine. So I love seeing undergrads at conferences like these. I brought two of mine myself. And they're both graduating in June of 2024. Wow, so if you don't have a job, this is your chance to get spotted. And yeah, without further ado, I'm just gonna give it to you. So good luck. Is it your first ever academic?
Yeah.
Well, good luck. You'll do great. You click on this button to advance to the next slide. Okay.
Sounds good. Thank you so much.
I'll let you know with the time constraint and like your minute left or so. Okay.
Okay, hello. I'm Wentao, as Esmer introduced, and this is Sam as well. And in collaboration with Yunpeng Luo and Faisal Shamari, under the supervision of Professor Alfred Chen, we'd like to present our work on understanding the internet-wide vulnerability landscape of ROS-based robotic vehicles.
All right, so just a quick overview on ROS. The robot operating system is essentially a middleware that facilitates the development of robotic software. And currently there are two major versions, ROS1 and ROS2. So as you can already see, like as robots are becoming increasingly common, ROS is being used more and more to develop these sort of systems, which means that attacks on these ROS-based systems can potentially lead to things such as physical damage, harm, and even loss of life. This becomes especially extreme when these robotic systems can be exploited remotely over the internet. And there have actually been examples of this already in the research community. For example, Demarinis et al. In 2019 were able to detect a publicly exposed robot and not only access its camera feed, but also manipulate its movements as well. And so we performed a two-part study as part of our research. The first part, which Wentao will describe, is to scan the IPv4 network space for publicly exposed ROS1 hosts. And then the second part is to kind of join or like examine the perspective of these victim robots, and by deploying honeypots with ROS1 and 2 applications and examining the network traffic they receive.
Right. So starting with our internet scan for ROS hosts. So for this part of the study, following the methodology of Demarinis et al., which is a prior ROS1 scan work, on the default ROS master port, which is 11311, we start by essentially attempting a TCP handshake. And then after that, testing that what's being run on is not a web server, just to make sure. And then sending ROS-specific commands to confirm the identity as a ROS host, and then to collect ROS topic, service, and parameter information about that specific host. We then manually inspect the collected data for common and meaningful identifiers indicating information about robot types and capabilities, and use that to construct queries that we can use to automatically categorize our scanned ROS instances. And in total, as with Demarinis et al., we performed 3 scans for ROS1 hosts, which were each performed approximately 1 month apart and also across several days between the months of September and November of 2023. So for our overall results, compared to the previous results, previous scans, which were at this point were performed around 6 years ago now, where they found an average of 123 hosts per scan across their 3 scans. We found 194 hosts per scan on average across our 3 scans, which is approximately 70% increase compared to that previous work. And so now we'll highlight some of the most notable robot types that we found. So this chart on the right shows the different robot type categorizations that we were able to identify. So it shows one category for simulations, and the rest are instances of robots of various different specific types, like cleaning robots and drones, all of which are highlighted in purple here, show no evidence of being simulations. And so we categorize them as likely physical. And so the first robot type we'll talk about is cleaning robots, which we found approximately 57 instances per scan on average, like the iLife brand cleaning robot vacuum cleaner, for example. So these cleaning robots are a type of robot that weren't observed at all in the prior scan, so these as a new finding, and this accounts for a significant portion of the increase in ROS hosts compared to that of the previous work, meaning the total ROS host numbers would be significantly closer to the previous work if we subtract this number of cleaning robots from that total on the previous slide. and then other notable cleaning robot types that we found, especially in terms of potential for damage if compromised, are drones, identified with topics like quadrotor and MAVROS, and also, which is a ROS package for MAVLink protocol communication. That's what MAVROS is. But we also have autonomous vehicles identified with capabilities like NUVO, which is a type of AI computing platform commonly used in autonomous vehicles, like with Baidu Apollo, as well as CAN bus and traffic sign, traffic light capabilities. And so with this, we see an overall trend of increasing deployment in home and industry settings robotic vehicle systems, especially with types like cleaning robots in home and industry environments, in line with the prediction that was made in Demaris et al. With the potential compromising of these systems by remote attackers, opening up more potential damage at a broader society-wide level than before.
All right, so for the honeypot side of our study, we set up honeypots running a very simple talker listener application. Specifically, we deploy 38 of these around the world on multiple cloud providers, namely Amazon Web Services, Google Cloud Platform, and Microsoft Azure. So you can see on the map, the blue dots represent the honeypots that we set up, and then the red points represent all of the different IPs that sent traffic to our honeypots. And just for some overall statistics, we received a total of more than 4,000 packets over the course of 1 month, and that results in an average of around 2.8 packets per day. You can see a few spikes on this graph, actually, and I'd like to point out this one specifically. One of our honeypots actually received a massive HTTP scan, and so we received a whole lot of influx of packets on that specific day. But just for the overall takeaway, we did not observe any malicious ROS scans, but we received potentially malicious non-ROS payloads along with potentially benign ROS2 scans, which I'll go over in the next few slides. This one, for example, the one on the left is an example of a potentially malicious RDP scan, as you can tell from the cookie MSTS hash parameter. And then the one on the right is a possible log4 shell exploitation. As you can see, there's log4 shell text in the payload text. And then for ROS2 honeypots, we received some example payloads as well. The one on the left is a payload from Shodan, a very well-known search engine. And then the one on the right is a payload from the Technical University of Denmark, who may have also been performing some ROS2 reconnaissance in terms of ROS2 host detection. And then just to wrap things up, we observed a significant increase in publicly exposed ROS hosts. And we plan on performing a future scan for ROS2 hosts in the future, since we only performed a search for ROS1 hosts this time around. And then 2, we deploy ROS honeypots to discover any sort of attacker patterns. And we received payloads from active ROS scanners, but also payloads that may have contained non-ROS malicious scans. The code and data for our study have been released on this website, as you can see here, just to benefit future researchers. And yes, that is our presentation. Thank you for listening. Any questions?
Nice talk. Thanks. I was wondering, when you are deploying such a honeypot on like Amazon Web Services or so, is there a feature that would give you like an arbitrary IP address so that it's not clear from the IP address range that you're not on an Amazon server? Because it would be quite unlikely that a robot is sitting in the Amazon network.
As far as I know, there's like an option where you can like allocate a sort of IP address. I'm not sure if that's the same across every single cloud provider. But for most of the cloud providers, actually, when you set up a cloud server, they automatically allocate an IP address for you. So it might be pretty difficult to change that.
Mm-hmm. Yeah. But you didn't see that actually some of the scanners would like not even touch you because you're like on a web services address where you're not expected to find a robot.
Well, yeah, we didn't really notice that pattern, at least from the data that we obtained. But yes, that could have been a possibility. Yeah.
It's not really a question. but it's more like I've looked at similar things. Like I love Shodan, and one thing you could also like look at is not only, I mean, you focus on robotic vehicles that run ROS, but if you like want to do some discovery and see like what's out there, I would try to look into maritime vessels. I've looked a little bit. There's a lot of interesting things about maritime vessels, and you can kind of like track maybe even certain vessels that are like live, because they obviously send their GPS via their telematics. So one thing you could do is figure out there's a couple telematics providers for maritime vessels. I'm not going to name them right now, but you can look them up. There's only a handful, and then you can basically using Shodan also like look. And just a recommendation, if you're like interested in this research, there's a lot you can do.
Sounds good. Thank you.
Thank you, guys, and
Thank you. Thank you.
Fantastic. Thank you. This was really refreshing, seeing something like this. All right, great job. If you don't have a PhD position yet, guys, I'm hiring, right? I gave you already your first project idea, so. All right, let's continue with Lewis Copeland. Is that pronounced right? Okay. Sorry about the hiccups with the emails.
Oh, no worries.
I like how particular you are. Are you German?
No,
Polish.
Polish.
Okay. Because Germans are, I'm German. They're very particular about. Anyway, Lewis Copeland holds a bachelor's degree in electrical and computer engineering from the University of Arizona, where he's also pursuing a master's degree, focusing on connected autonomous vehicle security under the guidance of Dr. Lazos. That's right. Okay. His academic and research interests encompass machine learning and communication theory, particularly as they apply to enhancing the security and efficiency of autonomous vehicle systems. And thank you so much. And here you go.
Thank you for the introduction, Mert. I'm here to present Cyclops binding a vehicle's digital identity to its physical trajectory using monocular cameras. At first, I'd like to take a moment to recognize that this was a group effort and recognize the contributors of this project. Cyclops was an effort that started in the summer of 2022 as part of a research experience undergraduate program at the University of Arizona. And during this time, I was acting as a graduate mentor for 4 undergraduate students who contributed on the project, and they're listed above. And the program itself was oversaw by Dr. Lucas Lazos and Dr. Ming Li. So this work is about connected autonomous vehicles, and connected autonomous vehicles themselves are complex cyber-physical systems who utilize communication theory and networking like V2vehicle or vehicle-to-vehicle communications and vehicle infrastructure to exchange information, along with utilizing control algorithms, computer vision, sensing, AI, and machine learning to accomplish unparalleled levels of autonomy, safety, efficiency, and comfort. And it's important to recognize that communications in particular play a safety critical role. Messages themselves convey information about the physical world and are taken as input into these decision-making processes. Some of these decision-making processes include longitudinal and lateral control, cooperative perception, platooning and maneuvering, path planning, amongst others that are not listed. Vehicles can convey their environmental observations, their vehicle state, and their intentions. For example, I am braking, I am changing lanes, and I am observing pedestrians crossing at the intersection above. Communication modalities are complementary to sensing modalities in that they experience differing delay, differing attacks that they're susceptible to, and differing effective ranges. So the traditional way to secure communication systems are legacy cryptographic tools such as message integrity verification and message authentication, source authentication. But today, these methods, especially for cyber-physical systems, these legacy cryptographic tools are insufficient in binding digital identities to the physical world. For example, let's consider in the figure above, we have a remote attacker who is claiming to be in front of the verifier, and this the remote attacker holds valid cryptographic credentials, but they hijack the identity of a legitimate vehicle on the road. While the victim itself can sense the vehicle that is there and use the traditional cryptographic primitives that are in place to verify the message integrity and authenticate the source of the message, there is currently no way to bind that digital identity of the sender to the physical location of where they claim to be. So the goal of this work is exactly that. It's cyber-physical identity binding. And let's consider that we have two entities, a verifier and a prover, where the verifier is claiming a digital and physical identity. We want the verifier to apply cryptographic tools to verify the digital identity of the prover, but we also want to be able to verify and associate the physical identity with his digital identity. The prover's digital identity could be any of the things listed below, from a digital ID to certificate or public key, where the physical identity can vary from ephemeral properties to non-ephemeral properties like vehicle class and license plate. So once again, the main idea is that the prover claims a digital and physical ID, and the verifier validates the digital ID and verifies the physical ID in a way that they're tied together. So how do we achieve this cyber-physical ID binding? Well, we propose this idea where the prover claims to be in a specific location following a specific trajectory. And the verifier must require that the prover provides proof of that physical trajectory. In our case, we use the surrounding dynamic environment to verify this trajectory. And we draw security from the spatio-temporal traffic randomness and uniqueness of the prover's point of view. So if I were to put this very simply, if we have the assumption that a verifier and a prover are co-traveling, then they should at very least observe the same environmental conditions, whether they're static or dynamic. We constructed the I primitive, which relies on the use of monocular cameras to authenticate the trajectory that the prover claims to have taken via looking at the dynamic traffic environments, or traffic conditions, from differing viewpoints. The prover and the verifier are traveling together, and they capture scenes synchronously, and the prover sends his images to the verifier, in which the verifier infers what we call the common field of view, which is the region common between both sensors, detects targets in that common field of view, and then determines if the scenes have sufficient matching between their features. So the common field of view is simply, like I said before, the region in which is common between both sensors. And in these two left images, we can show some implementation level calculations of the common field of view, where it depends on the intrinsic and extrinsic camera properties of each camera and each viewpoint. After we've successfully identified the common field of view, we can utilize target detection, and we personally chose an off-the-shelf machine learning or deep learning algorithm, YOLO V5, to determine all the vehicles in the image, and we kept track of their center bounding boxes, their width, their height, their class information. And now, how do we determine whether the scenes are a match or not? This begs the question. It requires a translation from the prover's image domain to the verifier's image domain, which is demonstrated as a high-level idea in the top left of the image. And theoretically, this can be done by performing a perspective transformation where we translate a bounding box from the prover's image domain to the verifier's image domain, utilizing a series of transformations facilitated by knowledge of the extrinsic and intrinsic parameters of the cameras from both viewpoints. However, we found in practice that when applying this perspective transformation, due to the accuracy that we needed in knowledge of these extrinsic parameters, which are the position of the cameras and the orientation, there were too many sources of noise in an application level to have reliable results. And the sources of noise included, driving on a rough road that would alter the orientation of the camera, or curvature in the road where the perspective was not maintained between both cameras. So to account for this, we propose a fuzzy matching method that operates as follows. It takes that common field of view that we referred to in the previous slides, and it partitions it into separate subregions. And these subregions act as a fuzzy way of characterizing distance and position of targets in this common region between the verifier and the prover. So, for example, in the figure to the right, we have this common field of view in each image domain of the verifier and prover, and we have boxes. We have cars that have been detected in the image domain, and we essentially want to assign those vehicles into the regions that they most likely populate in the physical domain, and then perform some sort of encoding, preferably one-hot encoding, to extract the entropy from the environment. So the process that we showed this far with the common field of view inference, the target detection, and the previous stage, which was the fuzzy matching, occurs on a scene pair basis. So it occurs on a scene-by-scene basis. So now we need to determine if the data that we have collected so far implies that the proof that the provider, or the prover, had submitted to the verifier implies that he coexists in the environment, therefore validating the trajectory. So this is this process. So for each scene pair, we do this scene matching, and we get a gamma value, which dictates whether that individual scene pair was matching or not matching. We then further subdivide those gammas into smaller groups to decorrelate from scene to scene, so there's no correlation from scene to scene. And we require this test assessment. We say we want alpha many of these scene outcomes, these matching outcomes, to be passing in order to accept this small test as a pass. And then of the like, a further threshold is applied beta, where we do the same thing on the subtests. Excuse me. And the reason why we structure a test like this is because our matching process is not particularly perfect. And with an alpha and beta, we can control whether a valid prover passes the test while maintaining that an adversary will fail. So the Cyclops protocol is an execution of a protocol between a prover and a verifier. I'm not going to go into the details of how the protocol works, just out of respect for everyone's time, but it is described in the paper. And in short, there's a digital identification phase that does that digital identification, and then what we just described with the primitive and the physical identity verification is the part that identifies and ties that physical identity to that digital identity. So we evaluated our protocol in two ways. One, we used Carla simulations, which is a well-known software for facilitating like research in computer vision fields, and on-road experiments. So the reason for us using Carla was to determine our alpha and beta and then apply them to the on-road experiments to see what type of results we got. And on our on-road experiments, we chose to drive up and down on a 3-lane each way city road at the U of A. And we mounted cameras on the prover and the verifier facing each other, and the scenes were not only time synchronized, but they were geotagged, and they had an application gathering information about the extrinsic camera properties as well. So in short, for our testing, we incorporated a remote adversary that was guessing how many verifiers, or how many vehicles there were in each of the regions based on a Markov chain that was formed off of the on-road, the data that was gathered on our on-road experiments. So we computed that the passing rate was a function of the fraction of tests that the adversary needed to pass, which is that beta threshold that we discussed. And from our simulations, we set the beta to 0.4 because that's where we observed that the valid prover was maintaining a substantially greater passing rate than an adversary, and the adversary's passing rate was nearing 0 or already at 0. And we applied this threshold beta to our on-road tests, and we varied our alpha over 0.3 and 0.5. And you can see that the valid prover passes far more often than the adversary, has a far greater likelihood of passing. So the final thoughts are, to counter emerging threats in cyber-physical systems, we must go beyond the digital security, and we have to bind those digital identities to physical identities. Cyclops is a form of cyber-physical access control, and we just showed how it thwarted adversaries, at least remote adversaries, from attempting physical ID hijacking. And there's significant room for improvement, such as other features to be used in the environment, other dynamic features to be used in the environment, more accurate target localization, or exploring the delay security trade-off. Thank you for your time. No questions? Okay.
If you have questions for the gentleman, please ask him. You have a question? So here's the thing. We're already in break, and we got to start the next session at 10 past, and we have one presentation left. And it's your student, I think, yeah. So, yeah. So, is Jim? Okay, perfect. So if you have questions for Louis, please, he's sitting there. Reach out to him. I have to unfortunately skip the questions here, so we can stay in time. All right. So Jun is our last talk. That's a short talk. She's a PhD student in the Lyle School of Civil Engineering at Purdue University. Her current research interests include cooperative driving automation, transportation system cybersecurity. And here you go.
Okay, so hello everyone, I'm Jun from Purdue University, and today I would like to present our recent work, which is modeling and detecting falsified vehicle trajectories under data spoofing attacks. So the cities and the transportation infrastructure are very vulnerable to cyber attacks. And also the cyber attacks on transportation system will directly influence the system safety and mobility. So reducing cyber risk is one of the primary concerns. And above that, the data spoofing attack is one major threat to cities and the infrastructure. So in data spoofing attacks, the attacker will deliberately manipulate or forge data to deceive a system and its users. It can be launched towards many vehicle and infrastructure applications. So for example, the attacker can generate falsified data to deteriorate CV or CV-based applications. And also the attacker can spoof the vehicle's onboard sensors. So in this work, we are trying to propose a generic anomaly detection framework to identify the abnormal trajectories from both known and unknown attacks. So here, the known attacks refers to the attacks that has been happened previously. So their abnormal pattern and the abnormal trajectories are known and can be used to train the anomaly detection model. And the unknown attacks refers to the attacks that may happen in the future. So their attack patterns are unknown. We selected two complicated and representative attacks like the ETA attack and the MSF attack for the attack trajectory modeling. So the ETA attack will generate falsified trajectories with abnormal longitudinal driving behaviors, and the MSF attack will generate falsified trajectories with abnormal lateral driving behaviors. We consider both attacks as complicated attacks that has taken into the vehicle dynamics and the vehicle kinematic parameters into consideration. And for the anomaly detection part, we utilize our domain knowledge to select the features from the trajectories and then train an anomaly detection algorithm. So we evaluate the model performance with both known and unknown attack trajectories. So first I will introduce the ETA attack and then followed by the MSF attack and the anomaly detection framework. So for the ETA attack, it will generate falsified vehicle trajectories that do not follow the longitudinal driving behaviors. So for example, as shown in this figure here, the infrastructure is collecting the BSMs broadcast by the CVs to generate an optimal signal timing plan. However, when the vehicle is under attack, it will send out falsified BSM trajectories that has an ETA longer than the ground truth. So this attack will lead to non-optimal signal timing plan and increasing vehicle delay at the intersections. So we formulate the ETA attack as an optimization problem to generate the attack trajectories. So the second model is the multi-sensor fusion attack. The MSF attack will lead the vehicle to drive off the road or onto the runway, and the entire MSF attack process is very time-consuming and complicated. So if we consider if we want to model the attack's impact on transportation applications, safety, and mobility, we only need the trajectory level attack behavior. And so in this work, we are modeling the MSF attack according to the trajectory level attack behavior. So we model the vulnerability profiling stage according to its lateral deviation magnitude and the duration of the vulnerability profiling stage as shown in the figure here. And for the aggressive spoofing stage, we use a family of exponential functions to fit the lateral deviation patterns. So the lateral deviation patterns remains consistent for the trajectories within the same driving scenario, but may differ among different driving scenarios. So in total, we use 6 different exponential functions to fit these curves. So in the anomaly detection framework, after collecting the ETA attack trajectories, the MSF attack trajectories, and also the normal car following and the lane changing trajectories from the historical data set, we propose a domain knowledge-based feature extractor that can map the trajectories to a feature vector, and then use this feature vector to train the anomaly detection framework. So given a new observed trajectory, the same feature extractor will be used to map the trajectories to the feature vectors, and then the pre-trained anomaly detection classifier will be able to tell if the observed trajectory is under attack or not. So to validate the proposed model, a highway segment with signalized intersection is built to generate the attack trajectories in the V2X application spoofing platform, also known as VASP. So there should be a video here showing the implementing the MSF attack on the VASP, but the video doesn't. It seems that the video doesn't work. So I will briefly introduce that. It is like we are implementing the MSF attack on the VASP platform, so the vehicle will first be guided to first fluctuate around the lane center and then gradually deviate from the road, which is similar to the original multi-sensor fusion attack. So we implement these attacks on VASP and collect the attack trajectories to validate our proposed anomaly detection framework. So the result indicates that the anomaly detection framework can distinguish well between the normal and the abnormal vehicle trajectories, with both low false positive rate and low false negative rate. And also to test the generality of the proposed model, we selected 6 attacks on the VASP platform to include the attacks on vehicle position, acceleration, speed, and also V2X applications. So the result here indicates that the proposed framework also performs well in detecting these unknown attacks. So in our future work, we are considering to add 2 types of baseline models for comparison. The first one is plausibility check-based model, which is another anomaly detection model that utilizes domain knowledge for feature selection. And the second type is a neural network-based model where the features are selected by the neural network and may not have physical meanings. So we want to see what are the performance of the two baseline models on both the known attacks and the unknown attacks. So this work is collaboration between Purdue University, the University of California at Irvine, and University of Michigan. And thank you. I'm ready to take any questions.
How do you know what is abnormal trajectory for ETA attack?
So like for the ETA attack, so for example, when a vehicle normally the vehicle will follow the car following behaviors like it follows its front vehicle. However, in the ETA attack, the attacker wants to generate a falsified trajectory with an abnormal ETA, for example. I think I have an example here. So like the vehicle, the actual trajectory is following like the blue curve, but it is sending out a falsified trajectory, indicating that it will arrive at the intersection maybe like 3 or 5 seconds later. And that will lead the vehicle to a brake even though there's no leading vehicle in front of it. So that is, normally we don't do that in the normal driving.
Thank you so much. First, last speaker. Unfortunately, you won't get a break because we have to continue with the next session. So this concludes the session, and I'm heading over to Louis, who's doing the next session. Thank you so much.
Thank you, everyone, and sorry that we're on such a tight schedule. We'll try to keep it going. So I'm Luis Garcia. I'm an assistant professor at University of Utah, and I'm going to go ahead and invite our next speaker up, Paul Agbaje. So if he could come up and we'll pull up those slides. Okay. Yeah, so our next talk is on learning driver behavior for auto theft detection and situational awareness. So Paul is currently in his third year as a PhD student at the Cyber Physical System Security Lab at UT Arlington, working under the guidance of Dr. Habib Olufobi. His research is centered around utilizing machine learning techniques to address data privacy and security concerns within vehicle networks. Yep. So go ahead, and I'll let you know when there's one left.
All right. All right, thank you so much. That was good with my last name. People used to have difficulties calling that. Thank you. And so I'll be presenting on AutoWatch on learning driver behavior with graphs for auto theft detection and situational awareness. I know for the whole of today, we've been learning about vehicle security, network security. Maybe we want to go a bit human to the human side of things. And our motivation for this work was really first thing was on vehicle theft. And we can see a snippet of different news articles on vehicle theft in the United States. Why are stolen car statistics rising? The second one is actually for a car theft that happened in 2022. And that someone was able to inject the control area network of vehicles using by removing the headlamp and inject SIM card messages to the CAN bus and then stealing the car. And this has been a concern, as you can see from the last snippet. That was from NHTSA, which says that every 32 seconds in the United States, a vehicle is being stolen. And most of it, about 74% of it, is actually passenger vehicles. And so it is important to find ways to kind of protect our vehicles. And the other motivation we had was on injuries on the road and deaths on the road. According to the World Health Organization, we have about 1.3 million lives lost annually on the road across the world. And 20 to 50 million people suffer injuries, and some of these are very serious injuries that that reduce their mobility or other things. And so it is very important for us to develop comprehensive techniques to kind of reduce deaths and also to reduce car theft. And that was why we tried to come up with some approaches that we can use to at least be able to detect risky behaviors, driving behaviors on the road, and also to be able to profile drivers. And one thing we leverage is vehicular data. Advancement in vehicular technology kind of allows us to have a lot of data on vehicles. And if we're able to get some of this data, like data from sensors like gyroscope and accelerometers, can we leverage this to model driver behaviors? And if we can successfully model driver behaviors, can we then use this model to identify or profile drivers and also to classify risky driving behavior so that we can alert drivers if they are making maybe sudden left turns, sudden right turns, or sudden acceleration or sudden brakes. And that was what led to AutoWatch. This is an overview of the architecture of AutoWatch. And we have data which we then extracted some features from. We established connections using k-means clustering and similarity matching. And then we use this to extract graph, which we feed to a graph neural network architecture. And then after we learned some latent embeddings, we feed this to a multi-layer perceptron, which then helps us with the downstream task of either profiling the driver or flagging risky behaviors. I'm going to go through each part of the architecture. And first is the feature extraction. Because vehicular data is highly high dimensional. One of the data sets we used had about 51 features. And so it is important for us to be able to reduce this feature space to kind of extract the very important features we need for our classification. And what we chose to use was principal component analysis as PCA, which helps to convert the data into PCs in a smaller subspace. And then the problem comes in how many principal components do you need to use for clustering and all. So you need to kind of choose the number of PCs that would explain the maximum variance in the data, that would capture enough information in the data. And so we use the cumulative explained variance ratio, and choose if the cumulative explained variance ratio reaches at least 0.7, then we choose those number of components for clustering. And then an example on this slide is the clustering we made with one of the data sets. You can see that it's we're able to cluster the data set after reducing the dimensions into 3 different classes. But the question is, how do we extract the graphs from these clusters? The first approach we used was cosine similarity matching, which is a popular approach in machine learning for similarity. And we assume that you have a budget. How many data points do you want to use for clustering? And we then, for each classes available in the data set, we choose B over C on number of data points, and then we use cosine similarities to establish intercluster and intracluster similarities. By intercluster, we mean similarities across different clusters, and intracluster is similarities within a single cluster. And then we just establish connections between pairs with the highest similarity. But apart from cosine similarity, we also use the horizontal visibility graph techniques to, because the data points, when you get data from vehicle sensors, what you have is time series data. And using visibility graph is a really nice way to convert this time series data into graphical representation. It kind of still keeps it keeps the order, so it does not change the orders and everything. And the way it works simply is that when you have on a time series scale, when you have two data points are connected when the data in between those two data points do not block their arrays, their views. So you have data point A and C, and another data point B is in between, but that data point B is shorter than data points A and C, and so you can establish connections between them. And so we're able to use this to establish connections between our time series data points. And this gives us a graph which we then fed to a graph neural network architecture. The one we chose for our work is VehicleSec because it can generalize to nodes that it does not see during training, and it is very efficient for large graphs. And the algorithm just shows an overview of how it works. You have a node in the data which aggregates features from its neighbors. You can go maybe 2 hops, 1 hop, but we went 2 hops in our architecture, and then it concatenates this with its own features, and multiplies it with some weight, and goes through some non-linearity. And then we use the produced embeddings and fed it into a multi-layer perceptron for the downstream classification task. And this is either used for driver profiling, again, or for the risky maneuver classification. For our experiments, we use 2 data sets. One is the popular driving data set from the Hacking and Countermeasure Lab. And this data set has 10 drivers and 51 features. The second data set is a data set for modeling risky driving behaviors. It has features from gyroscope and accelerometer data. And they use 3 drivers, I think, age between 27 and 37 or so. But between over 20 years and below 40 years, or 3 drivers. And we compared our approach with 4 approaches. One is support vector matching, decision trees, k-nearest neighbors, and a simple multi-layer perceptron. we converted the labels to numerical values and normalized, and then measured the performance with accuracy, precision, recall, F1 score. And this is a confusion matrix for both of these data sets. And we could see from, for the data set 1 and for the data set 2 that AutoWatch was able to really classify these different driving behaviors successfully for most of the data points. If you look at the second confusion matrix, you see that for most, for 3 of the risky behaviors, it got it was 100% except for the sudden left turn. And apart from that, in our comparison with other approaches, you could see that AutoWatch was able to get to 99.9% for accuracy, precision, recall, and F1 score, and up to 99.8% for data set 2. And we also showed a visualization of our approach, really what is the latent embeddings being learned, and how is it learning this for very accurate prediction. And we can see with the TASNE plot that it really learns embeddings in a way that it can really separate between classes. And that is a representation for the second data set, and we can see pretty well with the different colors that it was able to almost successfully separate different classes into different spaces. In conclusion, we will be able to present an approach that can, model the behaviors of drivers in a way that we can then use it for downstream classification for either driver profiling or for risky driving behaviors, and we demonstrated this with using 2 data sets. Thank you so much.
We have time for about 2 questions. If you have a question, you can line up at the microphone.
Yeah, really interesting work. So have you done the, any sort of calculation on the compute cost? Like what platform are you running this on?
Yeah, so we did this locally on the GPU, but I agree with you. We didn't do the computational cost on this in terms of time. But personally, one of my greatest worries with regards to the cosine similarity matching, that takes a lot of time, except if you vectorize your computation, which makes it a bit faster. But still, one of the things I was looking at is how to remove that cosine similarity matching from the process. And I was thinking if you could use, because we are using graph neural network to learn the embeddings anyways, if you use a graph neural network to kind of learn the connections itself, instead of using horizontal visibility graphs or using cosine similarities, which just shoots up the computational cost as high as possible. Another thing is, if we even decide to use the cosine similarity, we need to have a reasonable budget. The number of nodes we want to use for connections. We kind of went between 2%, 5%, 7%, and 10% nodes of the nodes for connection. And we still got good accuracies with this anyways, but the more nodes you choose for connections, the better your accuracies can be. But you kind of need to kind of find a trade-off between how much computation you have for your task.
Yeah, so stemming from that, so is there any reason you used like linear dimensionality reduction, like rather than using maybe an encoder, autoencoder kind of architecture to extract that initial features before feeding it to the GNN?
Is there a reason we used what instead of autoencoders?
So you use PCA to extract,
yes.
So it's a linear dimensionality reduction technique. So maybe some alternative options might be, I guess, autoencoder. Or some handcrafted feature, although I guess it depends on the domain. So any specific reason you use PCA?
Yes, the reason was because we wanted to go with something simple and straightforward initially, before then going to do something much more elaborate. Yeah.
Okay, cool. Thanks.
Great. Well, let's thank the speaker again. Okay. We're going to invite our second speaker up, just to stay on track. So our next speaker is going to be a talk on body posture analysis for human trust dynamics. So Sharon Lim is a PhD student at the Behavioral Research in Information and Computer Security Lab, BRICS, at the University of Washington in the Department of Industrial and Systems Engineering. Her research focus is at the intersection of human factors in cybersecurity within autonomous transportation and aims to design vehicle systems that can support driver response in the event of security threats. Prior to joining the BRICS Lab, she received her master's degree at Yonsei University in Seoul, South Korea, conducting research at the HFID lab with a focus on autonomous vehicles and extended reality. So if you want to come up.
Hello, everybody. Thank you for the introduction. My name is Sharon Lim, and I will be presenting our work in progress research titled Body Posture Analysis as an Objective Measurement for Human Trust Dynamics in Autonomous Vehicles. How do you want to
Is there? Yeah, where's the click? It's this one. Oh, okay. All right, sorry.
Thank you. All right, so the background to this research is that modern vehicles have evolved into these intelligent and autonomous transportation systems. However, this very computer-driven development also creates opportunities for unforeseen cybersecurity attacks on self-driving cars, whether it be in the form of code injection, GPS spoofing, etc. Current research mostly focuses on the technical aspects of autonomous vehicle security. So there does exist a research gap in the human aspects of AV security, especially when it comes to assessing and recalibrating trust in the aftermath of these cybersecurity attacks. And in this context, trust plays an important role in the acceptance of autonomous vehicles. And once this trust is degraded, it becomes very difficult to rebuild it to its original level. Therefore, there is a need to come up with robust methods to assess and recalibrate trust in AVs after these security threats do happen. Previous studies have widely used subjective trust questionnaires, but the drawbacks of these methods is that there are individual and situational biases. Objective measures, on the other hand, such as hand transition frequencies or eye glance patterns, they offer a more accurate assessment of trust levels. And to this end, our research aims to develop an objective measurement of trust based on body posture analysis of drivers. So to go on to the methods section of our research, we conducted a driving simulator experiment with 40 participants. Participants were first provided with an introduction to the study, and then they went through a practice drive so that they could familiarize themselves with the driving environment. And then they went through three drives. So first of all, the baseline drive, this did not have any cybersecurity threats. But in the attack drive, this did contain 3 cybersecurity attacks on the perception module of the vehicle, meaning that the vehicle wouldn't be able to properly perceive a traffic light or a crossing pedestrian, and it would just accelerate on. And then lastly, the participants experienced the post-attack drive, which was very similar to the baseline drive and did not contain any cybersecurity threats. I would like to note that the main results of the study are currently under review for the Human Factors Journal, and this was done in collaboration with Dr. Linda Boyle. To go on to the results, all of the drives for the experiment were recorded. So based on the recordings, we extracted 0.5 second frame images from the recordings, and then using the OpenPose library, we extracted key joints in the lower body from the images. We also defined some utility functions to extract and manipulate pose information and draw skeleton lines, as you can see in the top right corner. And then the angle between these skeleton lines were computed through vector operations and trigonometry. Based on this data extraction and manipulation process, we performed k-means clustering, especially to classify foot positions of the drivers. And this was done because we particularly saw that participants tended to move their feet the most in contrast to their head or their hands. And we also hypothesized that foot positions could be classified into foot on brakes, foot on the accelerator, the foot hovering between both pedals, and the foot completely off both pedals. And we could see some occurrences for each of these clusters, but we are in the process of studying for further validation for the accuracy and reliability of the clusterings. So to go into the discussion, based on this research, we would like to propose a trust assessment pipeline that is based on this analysis of drivers' body postures. And we do think that this classification can set the basis for further supervised learning algorithms, which can search for a correlation between these categorized postures and drivers' subjective level of trust of the autonomous vehicles. And in other words, the clustering and the labeling of these different postures can be used to identify patterns of trust, meaning that, for example, if the driver tends to have a lower level of trust, they would brake on the vehicle more because they would try to take control of the vehicle more, and thus they would be less dependent on the vehicle. This method can also be used as an objective trust measurement, meaning that the objective metrics derived from the posture and the movement of the driver's behavior, such as the skeletal angles. This can provide a quantifiable trust measurement and reduce the subjectivity from existing self-reported data. And this can also be used to adjust vehicle interfaces depending on drivers' trust levels, and thus potentially improve drivers' perception of safety of the autonomous vehicle. Lastly, this approach can lessen manual labor in terms of especially compensating for the traditional posture analysis that used to be time-consuming and required a lot of manual effort when doing the analysis. Limitations do exist in this research, especially in terms of misidentification of individuals and errors with skeleton detection. So future enhancements can incorporate other metrics such as distances to the brake and gas pedals to enrich the analysis. All in all, this objective approach to measuring trust through body posture analysis offers a foundation to develop trust recalibration strategies and driver adaptive systems in autonomous vehicles. Thank you.
Great. So we have time for about one question.
Very interesting presentation. I just have a quick question about, so in your case, your distrust or the level of trust is caused by the cyber attacks.
Right.
So how do you differentiate the trust variation caused by some other reasons, not necessary to be cyber attack, right?
Right.
If there's a deer in front of the car and it fails to stop, for example.
That was one of the, I wasn't able to mention it because of the time constraint, but we did provide a notification after the attack drive that this particular failure was due to a security attack, and it's not because of a mechanical failure or anything. So we did want to differentiate that the failure was purely due to a security incident and not due to any other traditional or existing failures that the vehicle could have experienced.
And do you include the non-cyber attack in the data set as well?
Meaning?
So non-cyber attack failures, so to kind of include that in your...
For this research, we weren't able to do that, but we do think that's one direction we could go into and see how these different kind of failures, non-cybersecurity attacks and cybersecurity attacks, do affect trust differently.
Okay. Mm-hmm. We're a little bit behind schedule, so maybe we could take questions offline. And we'll introduce our last speaker. I want to make sure we get back on track so that we can give people a break. They didn't have a break last session. So we'll have one more speaker. So our third talk is on adversarial object evasion attacks. So Rao Lee is a first-year PhD student in the College of IST at Penn State. Her research interest broadly lies in usable security and privacy in various settings,
So far, her work has focused on the intersection of human factors and security issues of emerging AI-enabled autonomous driving, especially in developing driver AI collaboration to enhance driving safety and security. So, yeah, go ahead whenever you're ready.
Hello, everyone.
Just use this for the clicker.
Okay. Hello, everyone. Today I'm very glad to representing our team to give you a small talk about our work. Adversary object evasion attack detection in autonomous driving context, a simulation-based investigation using YOLO. As we all know, autonomous driving system is typically following the loop here. At the beginning, we have the perception components, and then following the planning and control part. And also, SAE organization has a recommended definition for different levels of autonomous driving system. And we can notice that in level 3 autonomous driving system, human drivers are needed to take care of the uncertainty of the autonomous driving system. So when do we need the human's intervention and how? This is what we are interested in, and we want to figure out some loopholes here and fix it, and then to gear up the collaboration between human and AI. Let's start from the first part, the perception part. And nowadays, some researchers have shown the vulnerabilities of the machine learning models and AI, and some explore the adversary attacks for the perception components. But there are other researchers has proven that this kind of attack aimed at the AI component could not directly lead to the failure of the whole system. So understanding the impact on the downstream task is very important. Our current study mainly aimed to obtain an understanding of the detection distribution under different attacks. We mainly focus on 2 levels. First is the target object levels, and the second is the dynamic context levels. We mainly choose the state-of-the-art detector models, YOLO v5 and YOLO v8, to do the attack. We choose to detect the 3 widely investigated kind of attack: the stop sign, the vehicle, and the pedestrian evasion attacks here. And we mainly create our experiment in the color simulator. And we first do the static test here, which means we mainly put all the experiment elements in a stationary condition, and we only vary the viewpoint of the adversary object in the environment to see what will happen. And here I just show one part of the result, the vehicle evasion part. And here we can see that YOLO v8 definitely performed better than the YOLO v5, but both detectors failed to detect the back view of the vehicles, which might indicate that the viewpoint matters. We further evaluated the detection distribution in a dynamic context, which means we mainly collect our detection result when the Eagle vehicle was approaching the targets. And we mainly choose the 3 different locations on the color map to conduct our experiment to see whether the driving context can impact the detection result. Here, I just show one case, and we can notice that the red vertical line here means the minimum braking distance of human drivers, which includes our response and the reaction time. And the blue line here is the minimum braking distance of the autonomous driving vehicles. Yes, we can notice that there is a gap between those 2 lines, which means human drivers anticipated braking distance is much longer than the autonomous driving vehicles. So
Even if the detectors can detect the target in the autonomous vehicle's safety braking distance, but this can also influence the human driver's feelings because our human drivers is still in the car and it will anticipate a longer braking distance. So record the result we have here. YOLO could fail at a minimum braking distance anticipated by the human drivers. And also the context is critical factors in autonomous driving context. And also the viewpoint is very important. We need in the future we need to evaluate humans in our experiment to conduct further study. And thank you for listening.
We have time for one question. I'll ask a question. Have you considered, or I mean, this is a work in progress, so are you also considering how to model the human imperceptibility component as, you know, in your attack models, and, you know, how to do this in simulation, and maybe how to evaluate this component?
Yes, in our further study, we may want to add humans and factors in the driving simulator to conduct our further experiments to see for the perception components how human can help. Okay, thank you.
All right, let's thank all the speakers and thank you everyone for the great questions.
Good afternoon, almost evening, everyone. Welcome to the last session of the day, the third session on vehicular network security. My name is Hanif Rahbari from Rochester Institute of Technology, and thanks you all for joining this session. We have 3 talks in this last session, and the first talk is by Rick Chatterjee. He is a master's student at Colorado State University with the Department of System Engineering. His work is on security of commercial vehicles, mainly working on protocol analysis and binary reversing engineering. With that, I invite Rick for the first talk of the session.
Thank you. All right. I'm here to present our research on diagnostic protocol vulnerabilities in commercial vehicles. So moving over the agenda, we'll be showing 3 vulnerabilities in UDS protocols, which are defined in ISO standards 14229 and ISO 15765. The first goal is to go over the ISO protocols, especially in terms of UDS. So UDS defined in 14229 basically allows for diagnostic services for maintenance and service of commercial vehicles. And if you're familiar with CAN in general in passenger cars, commercial vehicles, and everywhere else, you generally have 2 parts to a CAN frame, an identifier and a data field. And UDS generally uses the data field of CAN to specify a lot of details for servicing and diagnostics. It also specifies multiple different types of frames, from single frames, first frames, consecutive and flow control frames. These are used to control the flow of data during a UDS diagnostic session. You also have the UDS transport layer services. As many of you may be aware that CAN is small. It allows only for 8 bytes of data load. And for data which is larger than that, which you typically need in diagnostic sessions, you have transport layer services, which allows multi-packet data transfer between ECU or electronic controller unit and the diagnostic tester, or the diagnostic technician computer in this case. It usually starts out with a single frame, followed by a first frame, followed by flow control frames, which allows the tester to basically control the communication between the ECU and the tester. And then consecutive frames and additional flow control frames are used to control transport sessions for multi-packet data transfer. Okay, Now, moving on to commercial in-vehicle networks, and what you see atypical in commercial vehicles is that you have ECUs in a commercial vehicle, which are usually nowadays connected through a diagnostic gateway for security and segmentation purposes to a diagnostic port, where usually you would find technicians sitting around and performing diagnostics. So what is the threat model here in terms of our research? Obviously, we don't consider anything that is plugged onto the internal secure network where all the vital ECUs are. We do think of a diagnostic attacker who would sit on either the diagnostic port or the telematics port, which is segmented out from the main network. Also to mention here is that we consider only protocol level vulnerabilities which do not involve any form of authentication mechanisms. Those have already been discussed in a lot of previous research efforts, and we go over vulnerabilities as defined in the protocol itself or protocol specifications that allow us to exploit certain things in vehicles. We did our experiments on both benchtop and experimental vehicles. We had 4 configurations of benchtop ECUs configured, as you can see in the diagram over there. We had a laptop which acted as our diagnostic tester. We had a laptop from where we performed attacks. They were all connected through a CAN backbone, and 2 different configurations of ECUs for 4 different test benches. And we did test all our attacks out on multiple different configurations of ECUs. And in each configuration, one was a target, the other one was a control ECU. So one was subject to attack while the other was not. We also did test out on a Freightliner cab test bench. This is a relatively modern truck test bench which we got in our lab, and I think it's from a 2018 model. It's relatively modern and atypical of modern trucks as you would find them on the road, although trucks do run for 20 years, so you can still find trucks from maybe 2005 still running on the road. But this is modern and probably the future that will stay on for the next 20 years. And inside this truck, we did find something which is relatively modern and which has been something that's been adopted by OEMs nowadays, which is to segregate your internal vital components from your external networks by means of a gateway ECU. So moving on to what makes our attacks unique and what's different. Like, I believe all of you here have heard about normal command injection attacks on CAN networks, and CAN itself is not secure by design anyway. It doesn't have any authentication mechanisms built into it, nor is there any encryption of data. But however, modern OEMs and truck manufacturers, and even in passenger cars, I believe, have gone through the process of trying to segment out networks through gateways, and this provides some form of network segmentation wherein your external attack surfaces are, even if they are not very protected, they still don't allow certain attacks to go into you or percolate inside the internal networks. What we describe in our case is something that can actually go over the gateway and get into your internal networks and actually affect them. So that's what makes it unique. So this is our testing setup which we had on the Freightliner test bench, and as you can see that we did test it out with a receiver on the internal CAN and a sender on the diagnostic CAN, and there was a gateway obviously trying to block out messages. And some of our observations were as such that normal command injection messages, as you can see on top with the attacker sending TSC1 messages, they did not go through into the internal CAN network. They were actually blocked out by the gateway. However, and this is by nature of design, that diagnostic messages are allowed by the gateway and are not checked at all. And they have to allow it for diagnostic purposes, otherwise vehicles won't run on the road and you cannot get your truck or car serviced, which is not something you want. So by design, this is a flaw, and this will be there. So gateways will have to allow diagnostic messages, and there is no throttling or sanitization for diagnostic messages being allowed into the internal network of vehicles, and this is what makes our attacks unique. Okay, moving on to the 3 attacks that we found on UDS protocol specifications. The first is the read data by ID attack. All these are denial of service attacks in some form or the other. The UDS 14229 specification states that when a read data by ID request is sent, the ECU must respond. And as in it states that it should access its data elements and respond with a specified value. So as such, sending a high volume of read data by ID requests can force the ECU to ignore other jobs and basically tend to those requests. This should lead to a denial of service attack, and that is what we observed on our 4 benchtop test bench. And as you can see that during the attack, on almost 3 of them, the messages from the target ECU dropped to 0 during the attack, except for one where it dipped a little as well, but not all the way to 0. But it did dip. And the significance of this can be vital because ECUs need some form of periodic transmission. When you have a big truck running on the highway, it's not that the engine just controls your everything. The brakes are also responsible, and it's intercommunication that enables the truck to function. It's important for braking functions, it's important for acceleration functions. So if a ECU actually does not send out periodic messages, the other ECUs may also not work as intended. We did observe the same thing on the Freightliner test bench as well. As you can see from the graph, and the dark blue line actually shows this, or dark blue bar, is that during normal conditions, there are certain messages on the bus. During a diagnostic session, those messages actually increase due to normal diagnostic activity on the network. However, during the attack, you can see that the blue bar actually dipped down. So there was a decrease in activity from the brake controller, or EBC, as shown on this graph, standing for electronic brake controller. Moving on to the next one is a session denial attack. And it is typical of a diagnostic tester and the ECU to establish a diagnostic session when performing diagnostic activities. And the specification states, and this may be due to resource constraints in embedded systems, that there shall exactly be one diagnostic session active in an ECU. So if an attacker actually hogs onto one session from a particular source address, there is a big possibility that a tester may not be able to establish a diagnostic session at that point of time, leading to a session denial. We did try it out with the attacker basically creating a diagnostic session and sending tester present messages to keep the session alive, and while at the same time with the tester trying to establish a correct or valid diagnostic session. We did observe that the diagnostic software during the attack was not able to establish a session. As you can see in the screenshot, the diagnostic software just said connecting and could not ever connect to the actual ECU when the session was actually being hogged by an attacker. And this can be impactful because if an attacker is there present during a diagnostic session, they may not be able to establish a valid session and perform diagnostics. The same was observed on the Freightliner test bench as well, and as you can see from the screenshot, it clearly says unable to read ECU data, check adapter settings. Adapter settings were correct, however, the diagnostic software could never establish a connection. Moving on to the third attack, and we named it diagnostic jam attack. And it's basically playing on the state system of an ECU, wherein a flow control frame is used to manage the transmission of multi-frame or transport layer UTS messages. The flow control frame can either have a clear to send, which basically tells the ECU, oh, you're clear to send data, or it could have a wait. Now, by design, I think it was thought about this, and there is a limit on the maximum number of wait messages you can send at a time. And if you send a number of wait messages one after the other consecutively, the session will be terminated altogether because you cannot keep a session in wait forever, basically. But what we thought about is that if we do actually send a pattern of waits followed by one CTS and then again a few waits followed by one CTS, this could actually hog up the ECU and it would get confused between these state transitions and actually not respond to other messages which are valid messages. So in our experiments, we basically have the attacker using the same source address as the tester, and the tester is in a normal communication within a normal diagnostic session. And what the attacker does is that they send waits, send a CTS, they again send a bunch of waits and a CTS, and the expected response is that during this period, the ECU actually gets confused, can't keep track of things, and basically it doesn't respond to other messages which are valid. The same was observed on the Freightliner test bench. As you can see from the screenshot, during a normal diagnostic session, it actually managed to get all the data using a normal UDS session. But during the attack, the data was just not present. It could not ever gather the data because the ECU was confused in these state transitions between weights and CTSs. With that, I want to conclude. We have 3 attacks, and also showing that gateways don't necessarily protect against diagnostic protocol attacks. Thank you.
So time for questions. So if there is none, I have a question. I ask you 2 questions. So you mentioned that the root cause of the attack, perhaps the main vulnerability, is the lack of perhaps throttling of the diagnostic messages. Do you have an insight why the standard did not put such a controlling mechanism in the standard? Was it like there is a trying to think of like what could be the solutions or the mitigation to this problem?
The mitigation may be to actually throttle, but I think the mindset was that diagnostics don't happen outside a shop when the vehicle is not running. So I think it's a general understanding that no one would exploit anything that's written in the protocols anytime. And diagnostics don't happen outside a shop usually, but they can happen. There is not the possibility that it won't happen ever.
So would it then be a sort of an idea to mitigate this attack? Like, if the diagnostic messages are sent outside the shop, then they have to be rejected, perhaps.
It may be, but it may be a difficult solution given that would need to map out diagnostic shops everywhere. The other mitigation could be to actually for the gateway to not allow these kind of things, or these kind of vulnerabilities in protocols need to be fixed in a way that you don't do these things. Like, for example, if someone hogs onto a session for a very long period of time, there has to be a way to identify whether they're actually doing something in the session or not, or just sitting there on a session not doing anything at all.
Okay. With that, thanks Rick for the talk. Thank you very much. I invite the second speaker for the second talk today. Yep, please come forward. So H.M. Sabir Ahmed is a PhD student in the Division of Systems Engineering at Boston University, co-advised by Professor Wen-Chao Lee and Professor Christos Kassandras. His research interests includes control and optimization, learning-based control, cyber-physical system security, and autonomous driving. With that, I invite you for the talk. Sorry.
Hi, everyone. So today I'll be presenting our work on secure control for connected automated vehicles. So to begin with, I have got here 2 videos. Basically, both of them have been simulated in traffic in Commonwealth Avenue, which is located in Boston, in the Boston University campus. So over on the left is what you see, vehicles are controlled using traffic light, and on the right, they are controlled using decentralized control. So what you should see in the video is that decentralized control has benefits, like it can reduce traffic congestion, leading to improved travel times, reduction of fuel consumption, so on and so forth. So these are the reasons for the idea of having connectivity and autonomy amongst vehicles. So this is the problem that we look at. We call this section that we specifically focus on a control zone, meaning that we will control vehicles when they are in this area. And then we put some rules in to ensure that the vehicles are safe. So what are the rules? First, we say, okay, every vehicle should stay safe to the car that is immediately ahead of it in the same lane. And then also we find the conflicting points within the intersection. So this intersection is signal-free, meaning that there is no traffic signal to control the flow across the different entries and exits of the intersection. So what we do is we identify this conflict point, and we say that at these conflict points, vehicles cannot come together, meaning they have to maintain separate distancing. And this is numerically imposed or mathematically imposed using a constraint that is imposed on the vehicles. Then we also have this roadside coordination, and what we use it for is to facilitate communication, leading, and also coordination. So basically, the cabs will share information with this particular coordinator, and the coordinator then assigns some policy to sequence the traffic by exchanging information or sending information to the cabs. So I will very briefly introduce this idea of these specific type of functions, which we call CBFs. And these are the functions that we use to introduce the constraints or the rules in the control zone in our controller. So the idea is if you have these constraints, let's say the safety constraints, what you can do is you can map them into another set of constraints such that the control input will appear. Control input meaning steering, acceleration, deceleration, and so on and so forth. And this has some specific properties, which I will also touch on briefly in the next slide. And this particular function has a hyperparameter. Let's call it alpha in this case. And then we can say that, okay, how about we choose a control that satisfies this constraint? What can we get from that? Well, we get this theorem that provides us the guarantee of basically satisfaction of the original constraint. So essentially, we have a sufficient condition, meaning that given we satisfy this new constraint, we will satisfy the original constraint. So here is the control formulation. We have our original constraints. What we do is we use these CBFs to map them into another set of constraints. We get our control for every vehicle. So the objectives in the control, we formulate it using optimal control. So we have some optimization. We say, how about we minimize the travel time and the energy consumption? And now coming to the advantages of the CBFs that I introduced in the last slides. So as you saw that this is a sufficient condition, so you get this provable guarantee on the safety. And also it provides some real-time computational ability, which is obviously suited for real-time, for autonomous vehicles. So here is a video of a test bed that we implemented using this particular control framework at Boston University lab. So we use these robots, which are, in our case, autonomous vehicles. And these are they all run their own controller. There is a roadside coordination unit, and it basically ensures that the vehicles are able to navigate safely through the road network. So this is a video showing the implementation. Now, what we were thinking is it possible that we can introduce attacks that can cause problem to this framework? So the first thing we looked at, we said, okay, how about we look at civil attack, and we say that there are some spoofed calves, and how about we set the intention such that they will prevent safe coordination, and they will also try to disrupt the flow within our control zone. And then we also consider another type of attack, because we are using communication between vehicles. So we said, okay, what happens if there is some uncertainty, but this uncertainty is controlled into information that is exchanged between the vehicles? Can we create issues by using these type of attacks? So again, the objective is, can we violate safety? So then we run our simulation. We did it in Carla, using Sumo as the traffic generator. And well, the video should be running. So yeah, okay. So what you see here is that this is an empty intersection and the vehicles will start arriving. All we do is we strategically choose some locations to spoof some cabs. And what we do is we say, okay, let us try to alter their normal trajectory and try to see if this can cause the other vehicles to slow down or to the traffic flow to get disrupted. And what you see here is the intersection is empty, but all the real vehicles are approaching slowly at the intersection because of the presence of these spoofed agents. So this is one of the things that Sybil attack can cause to the framework that I presented. Now again, the safety is not an issue. However, you have this issue of traffic flow disruption. So then I said, okay, the second type of attack was this controlled injection of perturbation because we rely on information of the vehicles. So we said, okay, how about we combine Sybil attack and we introduce some perturbations, but these are controlled, small amount of perturbations. And what you see in our simulation, this results in an accident. So then we said, okay, can we mitigate this? Can we address these issues? So we have our secure, robust, trust-aware control and coordination. So what we do is we incorporate an idea of a trust framework, and we say that we will compute the trust for every car in the control zone, and we use some specification. Now, these can be anything depending on the type of network one considers, but for us, we deem these as suitable. And we use these specifications to identify the behavioral anomalies in the cars in the control zone, and accordingly adjust the trust associated to them. And then what we do is we introduce this idea of trust-based coordination. So the idea I can describe with the illustration. What basically we do is we say that, okay, how about we find the calves that each car has to cooperate with based on this idea of trust? So for example, on the left entry, we have 3 vehicles which are indexed as shown here. So normally 4 needs to stay safe to 3 because it's immediately ahead. But we say that, okay, because 3 in our case has low trust, what we do under this framework is we say, okay, 4 has to cooperate with 3 and 1. And this is done through the control, so the decentralized control and the coordination. And another thing that we also add is, as I said before, there is this hyperparameter that we need to select for our controller. So essentially what this hyperparameter does is it provides this trade-off between safety, or in other words, how conservative a controller has to be, versus performance, meaning how much throughput you can get through your network. So what we do is we introduce this idea of trust in our constraint, incorporating it in the control, and then what we can do is, using this idea of trust, whenever we are cooperating with a vehicle that is not got high trust, we can prioritize safety, and when the vehicle is cooperating with a high trustworthy vehicle, then we can focus on performance, meaning throughput maximization. So essentially, we have an adaptive control scheme in our optimal control framework, and the adaptation is through this idea of trust between the vehicles. The other thing we said was, okay, what happens when you have this bounded perturbation or this control perturbation? And what I showed you in few slides back is that this can lead to accidents. So then what do we need is we need something that will guarantee safety within this bounded perturbation. So what we do is we basically modify the control, specifically the constraints, such that we get the guarantee, which basically ensures that given this perturbation is bounded, this modified constraint will guarantee the satisfaction of the CBF constraints, which in turn is sufficient to guarantee the satisfaction of the original constraint. So we have ourselves another sufficient condition. So these gives us the key results. So we get the safety guarantee with CBFs. Then what you do is you modify the constraints by introducing this idea of robustness into the constraints, and that gives us the safety guarantee against bounded perturbation. And then we also get, even combining these two, we get the safety guarantee against stealthy attacks, meaning attacks where we inject controlled bounded perturbation in the state or in the vehicle states. So here is the video again. What you see this time is that on the left, again, we had from a few slides ago, the attack resulted in a rear-end collision, but this time with the robust control, what you see is that the safety is guaranteed, thus validating the theoretical properties that I presented of the framework. So then what do? Is we said, okay, we have addressed the issue of safety. How do we mitigate this traffic holdup? So we introduced mitigation in our framework, and basically the idea of mitigation is to make sure that the traffic flow is not disrupted, and also there is guarantee in case we have any false positives. So we formulated as a optimization problem, and it essentially resequences traffic by adjusting the way they cooperate between themselves. And we also guarantee safety against false positive cases by using a simple observation model in our simulations. And what you see now are the two videos. Again, the left video is from a few slides ago, where you see the vehicles flow getting disrupted. But on the right side, you see with the introduction of this mitigation, we are able to address the issue of traffic holdups or unnecessary holdups. So finally, I have some plots which highlights the merit of the framework. So we basically have different percentages of spoofed cabs, and we compare our framework against three metrics, which is the travel time. As you see, it's improved. The energy consumption is improved, and also the fuel economy. And the main takeaways are we have this safety guaranteed control that gives us safety guarantee against civil attacks and stealthy attacks. And we're also able to mitigate the effects of attacks. The merits of our solution is that it's decentralized, provides provable safety guarantee, and it provides guarantee against false positive cases. So that brings me to the end. Any questions?
We have time for one question. So if there is none, here's my quick question. In your centralized, decentralized approach based on RSUs, do you assume that the vehicles that are in the control range of the RSU are fixed, meaning that the same vehicles stay for a while, or maybe your model accounts for vehicles coming into that region or leaving that region?
So the flow is stochastic, so we don't have any assumption on the certain presence of vehicles in the control zone. So the flow is stochastic, and we model it as a Poisson process, and they arrive randomly, and when they arrive within that zone, we basically will implement the control to ensure safety.
Okay, thank you very much. Thanks for the speaker. And with that, we move on to the third and last talk of the day. Our speaker is not able to join us in person, so we'll have the recorded presentation of the speaker, and the speaker would be available at the end of the talk for any questions.
Hello everyone, I'm Sampar Rajapaksha, representing Robert Gordon University, UK. Today, I am thrilled to introduce our latest CAN bus attack dataset collected from a moving vehicle designed specifically for intrusion detection system evaluation. This dataset wouldn't have been possible without the invaluable support of our industry partner, Horiba Maira, a leading automotive engineering and development consultancy based in the UK. Control Area Network, CAN bus, is widely used because it offers several advantages. It's cost-effective, supports speed up to 1 Mbps, has a lightweight design, and is highly robust. However, despite its widespread use, the CAN bus lacks security features like authentication and encryption. Additionally, its reliance on broadcast domain and ID-based priority makes it vulnerable to cyber attacks. As a solution, researchers have proposed intrusion detection systems. These systems are designed to identify attacks on the CAN bus. This slide highlights a range of common in-vehicle network attacks. Denial of service DOS attacks aim to disrupt communication services by flooding the network with a large volume of frames, typically with high priority IDs. In a fuzzing attack, a malicious node floods the network with a large number of frames employing randomly generated IDs and malicious payloads to mimic legitimate frames. This can include injecting valid IDs during normal traffic or generating entirely new random IDs. In a spoofing attack, the attacker targets specific CAN IDs to introduce malicious messages. Next, replay attack resend the previously valid frames at different times. For example, recorded speedometer values could be replayed at a later time. All of these injection attacks introduce additional frames into the CAN bus. However, suspension attack and masquerade attacks do not introduce additional frames during the attack period. Suspension attack involve compromising an ECU, preventing it from transmitting messages for a specific duration. On the other hand, in a masquerade attack, the attacker suspends an ECU and then utilizes a strongly compromised ECU to transmit malicious frames with the same ID and frequency. Generating real attack data on a moving vehicle poses significant challenges, primarily due to the high cost and associated risk involved. As a result, there are only a limited number of CAN bus attack datasets available to IDS evaluation. Some existing datasets, such as those produced by Hacking and Countermeasures Research Lab, have limitations. These include the use of high-frequency injection methods, making the attack easily detectable, as well as lack of benign dataset and the generation of attack data while the vehicle is parked. While the road dataset is considered comprehensive, it also has some limitations. It targets only a few CAN IDs, including only one low-frequent ID, and collects attack data while the vehicle is not actively driving on the road, but rather on a dynamometer during the attack period. This table shows the comparison between most commonly used benchmark dataset and our dataset, CAN-MyRGU. Accordingly, you can see that our dataset includes 36 attack log with 17 hours of benign data and around 3 hours of attack data with annotated labels. This slide provides an overview of how we created our dataset. We used a modern automobile manufactured in 2016. This was a fully electric vehicle equipped with fully autonomous driving capabilities. But for the safety reason, we deactivated the autonomous driving mode and used professionally trained drivers for both benign and attack data collection. You can see that the dataset collecting setup in this image, which is figure 1. We connected a Linux laptop to the CAN gateway through Kawasa Memarator and used socket CAN utilities for the data collection. For the attack frame injection, we use Python script created using the Python CAN library and the cancel command in the CAN utils library. We collected 17 hours of benign data over 6 weeks. During this time, the vehicle operated on public road in the UK, engaging a wide variety of normal driving activities. During attack data collection, due to the risks associated with injection attacks, the vehicle operated at maximum speed of 30 miles per hour on the proving ground of Horiba Maira. The image on this slide shows the 750-acre proving ground utilized for those experiments. For those interested in viewing this attack experiment, we have uploaded a video to YouTube. You can access this video through this QR code or the link available in our paper. We receive the access to the CAN data specification for some CAN IDs. Additionally, we observe the payload change using CAN sniffer available in CAN utils. Based on this knowledge, we created our attack scripts. We used two techniques to inject malicious frame. First one was the time-based technique. We injected malicious frames every 10th second. Second technique was the flam delivery. This means injecting malicious frame with the same ID immediately after the appearance of the legitimate frame. Accordingly, we used DOS, fuzzing, replay, and spoofing attack during our experiment. But suspension and masquerade attacks in our dataset were simulated due to their complexity requiring expert hacking and comprehensive vehicle knowledge. We simulated the suspension attack by removing legitimate target ID frames for a specific period of time. On the other hand, in a masquerade attacks, we removed the legitimate frames and only kept the malicious frames during the attack. Considering the limitation of the raw dataset, which was targeted only few CAN IDs and only one low frequent IDs, we targeted 13 CAN IDs representing high, medium and low frequent IDs. You can see these targeted IDs with red bars in figure 3, which shows the average number of ID counts for 1 second driving. On the right hand side figure, which is figure 4, you can see the frame transmission over 1 second for the targeted ID, which clearly shows the selected high, medium and low frequent IDs. This broader scope allows for a more comprehensive evaluation of intrusion detection systems. This dataset is accessible on our GitHub account with the link provided in the paper. Figure 5 shows the format of the dataset. This is available in the original raw CAN data format. We additionally included a label to indicate benign and attack frames. Additionally, we have provided a JSON file containing metadata for all attacks. This includes details such as attack's name, in this case brake warning attack, attack description, data log duration, attack duration, injected payload and ID, attack interval, attack type whether it's real or synthetic, and attack technique which are time-based or flam delivery. For certain attacks like denial of service and replay attacks, we didn't observe noticeable changes. This could be due to the changes not being visible or the CAN bus actively ignoring inconsistent messages for safety reasons, or perhaps due to payload used during the attacks violated the message checksum employed by this vehicle. Reaction to the majority of attacks were observed as warning messages, illuminated dashboard lights, and continuous warning sounds. But for some attacks, we observed significant behavior alteration. For example, gear shift attack that targeted the ECU associated with gear control, we experienced significant changes to steering wheel control. You can see that these changes in the uploaded videos. Since this dataset was equipped with autonomous driving capabilities, attacks of this nature on an autonomous vehicle could result in the vehicle deviating from its lane. However, there are few limitations available in our dataset. We could only drive the vehicle at a maximum speed of 30 miles per hour for safety reasons. Also, simulated suspension and masquerade attacks may not perfectly mimic real-world scenarios. For almost all injection attacks that we performed, the observations were immediate. Therefore, any IDS designed to detect attacks on the CAN bus should prioritize detecting the first instance of attack within the shortest possible time. As our dataset incorporates unaltered raw CAN data for both benign and attack instances, it is suitable for testing a range of intrusion detection systems. This allows for the evaluation of intrusion detection systems employing various features including timing, ID sequences, and payload data. We have already evaluated detection capability of these attacks using ID-based and payload-based AI-based intrusion detection systems. Some attacks are easier to detect and some are difficult to detect. Therefore, it is advisable to assess intrusion detection systems using all given attacks to conduct a true evaluation. Thank you.
Thank you, Samptha. So Sampath, who is the final year, who is in his final year of PhD at Robert Gordon University in UK, is with us now. Any question for Sampath? Maybe I go with a quick question, Sampath. For generating the attack scenarios, and you listed how you generate or what parameters you change, and two types of attacks. I wonder whether you have relied on certain existing attacks against these systems to generate or to generate the scenarios based on, or you develop your own set of attacks. Yeah, please.
Yeah, basically, can you hear me?
Yes.
Yeah, basically, we generate our own attacks. So we got partial access to the DBC file, and also we observe some of the payload data using CAN sniffer. Then based on that, we created our own attack. But the attack types are some popular attacks, like those sniffing, spoofing, replay attacks. But based on the CAN data specification, we created our own attacks.
So do you comment on how generalizable those attack scenarios are? And like, someone develops or designs a new attack and wants to test the attacks. Are the data set generalizable enough or general enough to cover such attacks, or like a wide variety of attacks?
Yeah, basically, actually, yeah, it's generalizable, and we targeted 13 IDs, and actually, I can release the attack script as well in our GitHub account. So it can be used for any vehicle if the data DBC file specification are known.
Okay, that's wonderful. Thank you very much again, and thanks for all the speakers and attendees for this session. We now end this session. This is going to be the last session of the day. We are not done yet with this symposium. We have the demo and poster sessions that start right here. Thank you very much.